Okay, so welcome to Time Series Analysis with Python. My name is Aileen Nielsen. I'm a software engineer at a company called OneDrop. We do diabetes management. We have a mobile app and a web platform. What it means is I look at a lot of time series data because, like many other chronic illnesses, diabetes is a stream of time series. How's your blood sugar? What kind of carbs are you eating? And it's a heterogeneous carb series, and it's an irregular time series because people don't do things at regular intervals, right? None of us do. Even if you have lunch at the same time every day, I can tell you none of our users are quite at the same time every day. So I think time series are really interesting. They're also really timely. So time series are something that's been around for decades and decades, and even some of the best stuff was done in the 40s and 50s. But they're newly relevant and newly challenging because the whole Internet of Things, big data, I would argue that everything is a time series. There is very little modern data collection going on where we don't in some way keep track of what we're tracking, right? So we don't just say, at my website right now I have 2,500 people, and then in an hour I have 2,200 people, because actually I have the technology to know how many of those people are the same, right? So as you know, just like with Google Ads that follow you around, or Bluetooth monitors that follow you around in stores, right? We are following individual actors right now. So almost all big data is time series data, or can be construed that way. So here's an outline of what we're going to talk about today. Why time series? A quick Pandas intro. I am not assuming that people here are full-time data analysts, so I'm trying to make this friendly also for people who use Python but maybe don't do data analysis. Then we're going to talk about dealing with dates in Pandas, reading and manipulating timestamped data, which as we know can be a pain in the butt in all languages. I happen to think Python is really easy and friendly once you get to know it, which is very nice, so I like people to become aware of that. And then we're going to talk about some common analytical tools for data exploration and do a little bit of prediction and classification. Some caveats to get started. Time series analysis is a particularly tricky and controversial field. I'm going to show you why in just a few slides. You need to read more if you want to do this, right? If you want to do this at work or at school and draw real conclusions or make real arguments, this is not going to get you there in 3 hours. This is to make you aware of what's possible and what's interesting. Test for goodness of fit, right? There's always the caveat, right? Your AIC is never good enough, right? You are a person and not an automaton for a reason. I feel that's especially true in time series. Domain expertise, especially important. You are trying to figure out how a process is working over time. So the more content you have, the more understanding you have of your system, the better, and the better informed your models are. Nobody can fix a lack of domain knowledge. And I'm going to be fast and loose today about assumptions that are required for models, etc. Whenever I don't specify but should, you should probably be thinking that things are IID, normally distributed, mean 0. If you're not a stats person, that just means it's a fairly normal type thing. We're not going to assume that things are dysfunctional or especially weird. And that tends to be true-ish for real-world data most of the time. So why time series? Where do time series pop up? Well, all over the place. Many of the most controversial questions in human existence, I would say, arise from time series. And if you see on the side, I've got two plots. On the top, I've got a plot of polar ice coverage over time. Worryingly, it seems to be going down, right? And it's a big question. Is it really going down? Are we fitting the time series properly? Below that, I've got a plot about whether crime is going down over time, right? Is it going down, or is that just a blip? These are questions that actually drive how our society functions, how we allocate resources, whether we call ourselves Democrats or Republicans, right? Is partly like what you think about these time series. So these things are everywhere. There's also speech recognition, right? That's another area. When you're thinking about how do computers figure out what you're saying or what you're going to say, that's a time series problem in another way, right? You could argue that a lot of natural language processing is a time series problem. That's one way to think about it. Science experiments also. These are actually taken from when I was in a physics PhD program. We used to just sort of pull on molecules and see what they did as we pulled. Nobody called it a time series problem, but that's actually what it was. We would run many thousands and thousands of 5 microsecond time series experiments. And we thought we were just looking for one feature, but really we were collecting data about time-oriented behavior. And of course, economics, government policy, right? Trying to predict what will happen. It's very important that we be able to allocate resources for our economy, for our government programs, etc. So the better we can predict things, the better we can run our country. Lots of people who work for the government actually spend their days trying to do these things, right? All these government actuarial type people, they're actually time series people. And finally, in the news, right? Many news stories you see that are about what's going to happen, they're actually about time series, right? So there was a lot of press once Donald Trump was elected saying what's going to happen to the stock market and looking at A, what happened in the stock market when past presidents were elected, and then sort of specializing, well, what happens when Republican presidents win, or what happens when pro-business candidates win? And then on the other side, you have a time series comparing how unemployed men and women spend their time, right? So you can also do sort of sociological type news stories looking at how do you spend your time, and that's a time series too. Final warning, be careful. Again, it's especially true for time series that you need to know something about your data. So what I've got here is divorce rates in Maine versus per capita consumption of margarine for the entire country. So you might try to gaslight me and say, well, maybe they really are related, but I'd say it's Maine versus the entire country. So apart from the margarine versus marriage bit, there's also the geographical mismatch. You can actually look at entire web pages that are full of these time series of these fake causation, correlation type things. They're pretty funny. I don't know how people have the time to find them, but just be very aware of that. And that can pop up even in your own work. So something to keep in mind. Okay, we're going to jump right into Pandas. Raise your hand if you have used Pandas at all. Okay, so it looks like 70-ish% of us have at least used Pandas. Raise your hand if you've used Pandas but you don't feel too comfortable with it. Okay. So we're going to blow through Pandas probably in less than 10 minutes. It's just to orient those who haven't seen it at all, to give you an idea of how it works, because we will be using it today. Okay, so let me just clear these. Okay. So here's our Jupyter notebook. And we're going to start by creating a data frame. So data frame is a little bit like an Excel table or like a SQL database of some kind. It's rectangular data. You can make a data frame in all sorts of ways. I'm making one with people's names, their ages, and their phone numbers. Every data frame has an index. If you don't know what it is, you can take a look at it. In this particular case, up here I actually assigned my index. It's important to understand that indices exist and that we can use them. We're going to use them today to index by time. So that's why I want you to know about indices. You can also create a data frame with NumPy arrays and column names. So that's what I did here. Same thing, right? So I have an index. In this case, I'm using names, and I can provide a list of column names in a variety of ways. You also have series, which is really just like a single column in a data frame. That's also really easy to do. Here's my series. And I can look at my series. And then you'll notice here my series is indexed just 0 to 5, but maybe I don't like that index and I want to change it. I can just directly assign to my index like this and rename the indices, as it were. And I can also, for example, easily detect where I have not a number style of data. Data frames and series also play nice with plotting, right? So you can just plot like this, just dot plot. It's a class method. You can plot a series. You can also plot an entire data frame. It will color things nicely for you, etc. You also get easy indexing, which is one of the nice things about both series and data frames. So for example, in my S data frame, maybe I only want things with an index greater than C. Boom, I can do that, right? So if I want to look at a subset of people by alphabet or by age or whatever, I can index on that and just very quickly select who I want. What if I just want data that's clean, that isn't null? I can do that too. What if I only want to look at one column? That's also very easy to do. And there are many ways to look at it, right? So I can either quote it in brackets or I can just access it like an attribute. Can also locate things by label. And what you'll notice here is even if I put in like column names that don't exist yet, it will play nice with it. So Pandas is just very forgiving. Good to know, meant to be encouraging for those of you who haven't used it before. And I can locate things by conditions, right? So let's say I only want to see the students who are over 17 years old, also very easy to do. Easy to summarize your data, right? So just like you do group bys in SQL, for those of you who maybe have used SQL but not Pandas, it's easy, for example, to get a mean on a column. a max on a column, a min on a column. Let me just actually put my data frame here so you remember. So that stuff's super fast. I can also easily add columns like this. I can very quickly, for example, find out who had the highest grade, super fast. I can do group bys just like with SQL. I can group by age and then get a mean of some other characteristic. I can also bin things on the fly, right? Create categories on the fly. So if I wanted to do that, I easily could. And finally, I can do things like apply a lambda function really quickly, right? So if I just define a lambda, here you can see I want to just age up my students by a year. Boom, it's done, right? And there are my students. Instead of 17 and 18, they're 18 and 19 now. A couple of built-in methods that you should be aware of, we'll use a lot today, and that are just handy are mean, counting, correlation, and qmax. Okay, so if you have questions about Pandas as we go, I think the best thing is to just treat each other like a resource. You don't need a ton, but it's a good tool even if you're not a data person. Okay, so that's our Pandas. So now we're going to talk a little bit about dealing with time. So we're going to jump right into the second notebook, dates and times. And we're just using Pandas. I don't even know if we're actually using NumPy. Pandas just has an enormous quantity of time-related functionality. I would encourage you to look at the docs, but I want to show you some really nice things. So the first thing is we can easily generate series of times. I can specify a start date and the number of periods and the frequency. So if you look at this one, it reads very nicely too, right? I have a range, and I just want to go from July 15th, 2016 at 10:15, 10 periods, and I want frequency of M. What do you guys think M is? Monthly, probably, right? We can always confirm. And here we are. I've got 7/31/2016, 8/31/2016, 9/30/2016. So what kind of monthly is this? Yeah, last day of the month, right? There are ways to set it to be first day of the month, right? You just look at your parameters. You can get first day of the month. You can get 17th day of the month, right? It's all about just knowing what parameters to adjust. But what you'll notice right away is it takes human time, right? Which is what we want, right? When you're dealing with time-stamped data, maybe you're doing science experiments and you've only got to deal with 20 microseconds at a time. If you're dealing with anything related to humans, you're going to have to deal with calendars, and that's what Pandas is really built for, right? So I can have a monthly frequency. What other frequency might I like? Maybe I want a daily frequency. Now I've got daily frequency. What's this one? Put in a B. Biweekly? Well, I went from 7/15/2016 to 7/18/2016, so I didn't skip a week. 7/19. Weekdays, business days, exactly, right? So it's got a lot of functionality to deal with business-related things. You can define a custom business calendar. You can use a standard business calendar. So you can do things that will, say, match the stock market or maybe match your company if your company only does Monday to Friday, et cetera. Okay. So I don't know if we can all look at this at once, but I just want to make you aware of some of the parameters, right? So a date range, you can specify some of these. You don't have to specify all of them. And if you want to know how many of them you need to specify, you just have to think about it logically, right? So would I specify a start, an end, number of periods, and frequency? No, why not? It would be overspecified, right? So it would probably forgive me if they're all consistent, but if they weren't all consistent, it's going to throw an error, right? Like if I say I want to go from May 17th to May 19th at a daily frequency and I want 20 periods, Pandas is going to come back and say, well, that's not actually possible unless you want me to do some bizarre time-traveling nonsense. So it will not let you do things like that, which also means that you can be lazy, right? We've all been in a situation where it's sort of like, I don't really want to figure out what those dates are. I want someone to do it for me. Welcome to Pandas, right? Pandas is actually now taking care of that for you. So of these four, you need to give it enough to know what dates to actually generate, to have it be determined but not overdetermined. There's also things that are just extra nice things, right? Like closed, make the interval closed, right? You can do left, right, or both. That first of the month, last of the month. beginning of the day, end of the day, beginning of the business day, end of the business day. You can name your index, say if you are going to use a series with a named index, for those of you comfortable with pandas. And this one's also nice, time zone, right? I don't know how many folks have worked with time data in the past. Time zones are a huge pain in the butt. And let's also remember daylight savings, which has to do with time zones. Pandas takes care of all of that, and we'll see a bit more of that later. But it's just really beautiful as far as how effortless it can be once you get comfortable with the API. So where did my notebook go? Here we go. Okay, so there's our timestamp. There's our date range. Now, what if I just want one, right? Maybe I don't want a range. I just want one moment in time. Well, that's a timestamp, right? So pd.timestamp, I can do this. What do you notice about my pd.timestamp? There's a couple of things to think about here. It gives me the time of day, exactly, right? So a timestamp, I might just specify it as July 10th, 2016, but actually a timestamp is a point in time. It can't just be a day. That would be more like a time period, and we'll see that soon. But a timestamp is a specific moment in time. In Pandas, they're actually specified down to the nanosecond. Some people actually do use nanoseconds. For the rest of us, we can ignore that. But you do need to specify something sensible. If you don't, it's just going to put you at midnight, right, with the zeros. So you want to be aware of that. So there's my timestamp where I've specified time of day. How far do you guys think I can go? Although I actually told you. Nanoseconds. So how am I going to do that? I've got 10:15:15, which 10:15 a.m., 15 seconds in. What if I want 15 seconds and 1,000 milliseconds? Well, you can't have 1,000. 999 milliseconds. Decimal, right? 0.999. There we go. And look, you see actually how it starts adding. One thing also to be aware of, I don't think this has been fixed. It displays up until the 6th decimal point, but it actually does store up till the 9th decimal point. So just a weird glitch in case you ever are checking. Okay, and well, here we see how much detail can you add, right? 056, that's 3, 757, that's 3, 57. So if you force it to go out to beyond the 6 digits, it will display. And those are always there. Okay. Now, I don't know if we've got any non-Americans in the room. Maybe? Okay. So you guys will be especially interested to be thinking about what's going on with these strings here. So Pandas is very forgiving as far as you can pass it all sorts of things that feel intuitive to a human, talking about the day, and it will process them. But is it going to do it in the weirdo American way or the non-weirdo, non-American way? The rest of the world way. And in particular, I'm looking at these. So go ahead and experiment if you have the notebook open and tell me which, is Pandas universal or is it this snarky American format? It's American. So we've got 7/1/2016 versus, let me put this down, 1/7/2016. If I want to test which one it is, let me go ahead and put in what as an American, what I would think the date should be. And which one does it match? It matches the American formatting. So that's just something to be aware of. You could also just get caught unawares. One very cool thing is if you have a date that's not ambiguous and you put it in European format, Pandas will catch it and fix that, or not fix it for you, but it will know you're using European formatting. But in a case like a 1 and a 7, it will assume American. There's a day first parameter you're going to want to set if you are using more standard non-American dates. So again, just shows how beautiful this API is, how much detail and thought went in, although it does favor Americans a bit. Okay. What are some properties of timestamps? Let's go ahead and look at the time date components. You can see all sorts of things, if you click on that link, that are just waiting for you. So all sorts of things you might normally need to figure out, right? Like if you work in finance and you need to know what quarter a date belongs to, it's there. If you work in health informatics like I do, we care a lot about what day of the week it is because people tend to behave consistently, right? Maybe people are stressed on Mondays and more relaxed on Fridays, and on Wednesdays they eat too many calories or whatever. So I can get a day of the week very easily with .day of week. You can also get day of year, right? So if you find that people behave seasonally, it's very easy to match these things up rather than having to compute it yourself. So that's very, very handy. Whenever you're wondering, how do I get this thing, chances are that Wes McKinney and the other folks working on Pandas have already put it in for you. So those are timestamps, right? So just to give you a demo, right? What's the quarter? July 10th apparently is the third quarter. And this is just an example of a really smooth interpretation of the data. Okay. Any complaints about timestamps? Have I sold, like this is just a solution to all your problems? I'll tell you no, because I have the solution to all your problems in the next section. So what do you not have yet? Yeah, you don't have intervals, right? So you're like, yeah, but most of the time I don't meet my friend exactly at like May 17th at 1:45 p.m. Oregon Central Time, .0004 nanoseconds, right? I mean, usually there's some understanding. Meet me in the next 5 minutes, or like this tutorial. The understanding is it's going to be about 3 hours, right? So we care about intervals. Part of the way we get there is first we need offsets, right? We need this idea that there's a starting time, and then we add some component of time. So first you've got time offsets. These are time deltas with a lowercase d. And here's an example, right? 1 day and 1 microsecond, and there it is. 1 day and 1 microsecond. 1 day and 1 millisecond. There it is. 1 day and 1 nanosecond. It's there, you just can't see it. Okay. PD.timestamp can be added to PD.timeDelta, right? So if you have a timestamp, you can just add a delta to it very intuitively. Here's an example. I've got July 1st at 8 a.m. and I want to add 1 point at 5 hours, and that gets me to 9:30, exactly as it should. PD.timeDelta, 15 nanoseconds. Showing up as a 0, is that a bug? No, right? It's actually there. It just prints as 0. I'm probably harping on this bug a little too much, but for those who do use nanoseconds. Okay. Range plus PD.timeDelta 1 day. What did I do here? I took my whole range of dates rather than just a moment in time, right? So a time delta can be added either to a timestamp, a single moment in time, or to a time range. Now you might feel like, well, a time range is probably just a list of timestamps, so what's special about it? Well, is that really true? No, because it's got a frequency, so that's something to keep in mind. The reason a time range is a time range is it's got a frequency. It's not just an arbitrary collection of timestamps. If you want an arbitrary collection, you can just generate your own. And now we get to our intervals. So we've got time spans. These are called periods. So let's look at PD.period versus PD.timestamp. We've got a period 7/2016. Again, it's American style, right? So that doesn't mean like, well, I don't even know what that would mean as a non-American style. But we've got July 2016. We've got a timestamp. If I want to check if that time is in that timestamp, I check whether it comes after the start time and before the end time. So just like a timestamp, a period has all sorts of useful attributes, such as start time and end time. Just like I have date ranges, I've got period ranges. A lot of the stuff that's built in Pandas is there because it's going to assume you want to index data by time. So all sorts of things are built ready to be indices. So here I've got PD.period range. We'll start from the 1st of 2016 at 12:15. I want an hourly frequency. 10 periods. Here are my periods, right? So how do you know it's a period and not a date range? Well, it says period. Otherwise, it looks very similar, right? They play nice in exactly the same way. I've got my frequency. It lists it out in this very human-readable format, etc. I can also do 60T, right? That's just 60 minutes. And what do you notice is different here? So I did a period range. I have the same starting time. I did a frequency of hourly versus a frequency of 60 minutes. Yeah, so what's going on is here, it's on the hour, because we looked at before, right? It sort of picks a logical, sort of human-friendly thing, right? So like when we looked at the monthly date range, it always just goes for the last date of the month, or it can go for the first, but it's going to pick some sort of nice round point to benchmark you. So that's what it's doing with hourly. On the other hand, with minutely, it's going to stick to the minute you gave it. Okay. And this is the same. Okay. So we looked at how you can determine whether a timestamp falls within a given period, but try to remind yourself how you would do it. Try to do it before you load the snippet. Okay. So if I have a period, I have a start time, I have an end time. How do I check if a timestamp is within? Greater than start time, less than end time. Exactly, right? So that you do have to write out for yourself. Okay. We've also got combos. So I also want you to be aware when you've got these offsets or frequencies, you don't have to use nice round numbers like 60 minutes or 1 hour or 1 month. You can arbitrarily combine stuff, right? So if your boss comes in and wants customer stats on your website every 2 hours and 20 minutes because that's what his hairdresser suggested that morning, you can easily do it. So all those really annoying arbitrary demands or seemingly arbitrary annoying demands become very easy, right? So, oops, look at that. So you can easily compute whatever frequency you want. Just good to be aware that everything your heart could possibly desire with time-related data is super easy to do. Okay, so how do I make a pandas time series with some of these aliases? Well, we have already done that, but here are a couple of examples. And what's special now, versus I've just been showing you date ranges and period ranges, right? So there are ways to compute moments in time at periodic intervals or periods that cover periodic intervals. Now what I've done is I've made a pandas series indexed by a period, right? So now I have a pandas series where each value, these I just randomly counted from 0 up, I believe, is indexed to a time interval. So instead of indexing students' grades according to their names, I am now doing the exact same thing, but I am indexing values according to time of day or day of the year or what have you, right? So I've got July 1st, 2016, 11:15, the value was 0. July 1st at 13:15, the value was 2. I now get all that nice pandas functionality, for those of you who are comfortable with it, with time. I can do the same thing. Now I'm going to do one that would normally be really messy. I'm looking at 60 business days at a time, and again, I can just index with time, right? I can now know that my values correlate to a particular time interval, right? So like 8/25/2017, it was 5 for the next 60 business days. That's the interval. So how do we index a time series with a date range? I showed you above here with a period range. They're very interchangeable. Instead of a period range, I just type in date range. And what that means is I'm going to have selected time stamps, a specific moment in time, indexing my data, rather than an interval. So you have to think about which of these is appropriate for your data, right? Are you doing something like monthly counts? Or are you actually saying, at this exact moment, I just did a count, right? At this exact moment in time, I counted people on my website versus over this month, I counted people on my website. Okay. So what are the different use cases? Well, here's an example. I've got TSDT, so that's the one that was defined with the date range. It's indexed by moments in time, not intervals. If I do TSDT and I try to index it by July 1st, 2016, 11, I get this one thing, 11:15. If I do the period, what do I get? 2016, July 1st at 11 to 2016, July 1st at 13. I also only get the one thing. But it's overlapping time now rather than a single moment in time. Okay. If you need to convert between a date time index and a period index, you just do 2 period or 2 timestamp. Super easy to remember, right? So a lot of this stuff you'll find you just play with it for a day or two. It just sort of starts rolling off the tongue because it's very sort of natural language driven as far as the names. Okay, so I'd like you guys to try 2 things. First, go ahead and try to create a timestamp with European style formatting. Good to be able to do that. And also figure out how you can generate a string representation of your timestamp. So I'll just put 2 minutes on the clock for that, and then we'll talk about it. Okay, so it's sort of been 2-ish minutes. How do I set that day first flag? Did anyone do it? Yes. Okay, so day first equals true. So, it would help to spell timestamp correctly. So if I am American, actually this doesn't make sense at all. If I'm American, I'd have to reverse it. But if I am European, what's this date? Is it November or September? September. Am I really using the day first bit right now, though? No, right? So I have to, if I want day first September, I want to do it this way. Is this is November for European. And what's this? This is September. Okay. So day first. Oh. Oh, thank you. Thank you. Okay. Let me just get my snippet. That's probably better. Okay, to date time. Here we go. Here's our day first. Thank you. And then string from time is the other function you want to be aware of. And here's your format. Say if you wanted year to month to day. And we can take a look at these and see how they look. Okay, so questions about this? Are we sold on Pandas time functionality? Best thing ever? Made your day? That it's so easy? Cool. Okay. Let's also talk about the usual pain in the butt of time zone handling. Something Pandas has really just done a wonderful job of making a non-issue versus the nightmare it might be if you don't use Pandas. Okay, so first we'll generate a date range. So we're just going to have March 6, 2016. I want 15 periods. I want a daily frequency. If I look at my range, I've got my range. If I look at my time zone, I'm not printing anything. Why is that? Come on. Maybe I need this. None. Okay, well that's why my Jupyter Notebook wasn't outputting anything. I've got no time zone because I haven't set a time zone. So that's handy for two reasons. One, you can have a time zone naive object, so that might be helpful, right? Maybe you actually don't care about time zone. Maybe you're a sociologist, you're studying what time people eat. You don't care where they're eating, what time zone. You want it to be naive. It's really convenient that you can keep it that way, right? It's also really nice that it doesn't automatically send you to UTC, right? So anyone who's sort of like, as one of their first computer projects, started working with Postgres or MySQL and everything's in UTC and you didn't even know it, so you put in one date and you get out another and you don't know what's going on, it also helps you avoid that trap. So it won't give a time zone if you don't give one. It won't sort of stick you in and make it the wrong time. And it also respects that sometimes you have data that doesn't need a time zone. On the other hand, if you do, it's really easy. You can just put it in your constructor as a TZ. And there's your time zone, right? So that is very easy to do. If you are ever unsure of what time zone you want or how it should be spelled, you can use the PyTZ package. It's very easy to get common time zones, of which, according to the package, there are 436. Let's just look at a few of them to give you an idea. It's not hard to be a common time zone. There's definitely more time zones in the common than I have ever heard of. But there's actually also like an additional 150 or so that are not common. So just be aware of that. Those are already in Python for you to use. What are some time zones that aren't common? Well, apparently Indianapolis, Mendoza, etc. Okay, so how are we going to localize a timestamp? We're going to start with a naive timestamp, pd.timestamp. I've just made a naive timestamp. If I want to localize it after it exists, right, let's say I miss the ability to pass it in the constructor, I can just do .tz localize, pass in the name of my time zone, and I will get a timestamp with that time zone. I can also convert. If it already has a time zone, I can convert. So we've got T, which now has a time zone. It's in US Central. What if I want to put it on Asia-Tokyo time? Well, I can do that. And what do you see has changed as I went from T to TZ convert? It converted the time. So it doesn't just change the label and leave the time of day. That's the thing to be aware of. It actually updates the time, which I think is what you'd want to do. That's the more difficult task. If I just wanted to change the label, I could easily just have set it myself to begin with, right? So this, once you give it a time zone, you fix a real moment in time anchored to a place, and then whenever you adjust it, you're adjusting relative to that time zone. If you have it naive, you're always just going to have that label of whatever time you said it was. Okay. What's the difference between TZ convert and TZ localize? We'll try to run TZ convert on a naive timestamp. What do you think is going to happen? It'll throw an error, right? Which is what you'd want it to do. You have a valuable object when it's time zone naive, right? That's a legit way to want to store your data. So you wouldn't want to just randomly slap a time zone on without being aware that you weren't properly converting. Okay. There's also some fun with daylight savings, right? You will get weirdness with time zones based on daylight savings, but you now don't need to deal with this problem yourself. Pandas takes care of it. So let's look at the date range from March 10th, 2016, 10 periods, and take a look at what that looks like. What do we see here? We jumped, right? We had our daylight savings time and we jumped. Pandas is aware of that. It will take care of that for you. Be aware of that, right? It's not going to not do it either, right? You'd have to go out of your way to have it not take into account daylight savings time. What else do you notice then? This will just default to daily period. The reason it defaulted to daily period is that's the level of specificity I gave the date range, so just pointing out another helpful feature. If I don't give it a frequency, it says, well, if you talked about a date, you must want daily. If you gave me an hour, you must want hourly, right? More intuitive functionality there. But what do you notice? Did it really give me daily? Or did it? Because it went from 5 to 4. So in what sense is that daily? 24 hours later is one way to think about it, and another way of expressing that is UTC, right? So whenever you're sort of not sure what it would do, think, well, what would it be in UTC? What would it be in sort of a non-dysfunctional time zone? And that's what it's also preserving. So those are the two ways of thinking about it, and they're both consistent. You will sometimes run into ambiguous times, however. So let's take a look here. I've got range hourly, which I have as range hourly. Let's take a look at what it is. So we've got November 6, 2011. I go from 0 to 1 to 1. Why is that? Well, because I said it that way. No, I said it that way. If you look at the list, it's time zone naive. But if I localize it, I get an ambiguous time error. Why did I get an ambiguous time error? Well, yeah, so some of these are maybe the same time, right? Maybe something really weird and dysfunctional is going on with this 1 o'clock thing. So let's figure out how we can deal with it. How do we deal with the ambiguous time error? Well, actually, you can try using the ambiguous argument, right? So when you make this error or you run into this issue, it will actually tell you how to fix it, and it will do it sort of the intuitive way that I would personally fix it if I knew the problem myself, which is this. So what did it do? What happened here? So it's 1 o'clock. That part is still kind of dysfunctional and weird, but it went from -5 hours to -6 hours. So it recognized that what I was trying to do was account for the fact that we had fallen back, so that we actually did have that 1 a.m. twice. I want to express that with a label, but it says, hey, once I disambiguate this and relate it to UTC, they're actually 2 different hours. So boom, it takes care of it. Hopefully you'll never have this kind of esoteric problem, but if you do, it's really nice that it's taken care of. And you can see here, if I just convert it to UTC, it is now nice and functional. It's 5 o'clock, 6 o'clock, 7 o'clock, 8 o'clock, 9 o'clock. So very nice to work in UTC when you can. That is how Pandas does its thinking, right? It works in UTC, which is really just a way of saying it works on time that isn't shifting around depending on the calendar day, etc. Also, Pandas goes to amazing lengths to try to figure out things for you, right? So what's going on here? I've got March 13th, 2016, U.S. Eastern, non-existent time error, right? So it will catch really funky things that you're doing, right? I think there was never a 2 a.m. on March 13th, 2016 because of the time change, right? We probably just went ahead to 3 a.m., right? Because it's spring ahead in the springtime. So it will figure things out like that. Yes? 3-4 for the hour. It says it's 3 a.m. 3:24 a.m. So it gives you the UTC time. You guys probably have a nice... Yeah, I'm 0.20.0. What are you? So you've got Windows. You look like you've got a Windows 2. What's your version of Pandas? Oh, so maybe they made a different decision about what would be logical. But it's 3. Let's talk at the break if one of you can show me, because I'm really curious. But the idea is there are weird times that either don't exist or have weird meanings. Pandas does its best to try to help you and give you sensible output. That we can summarize. We'll follow up on the new functionality. Okay. So let's also talk a bit about how you read in data, right? Usually when you're going to work with time series data, maybe you'll do something like download stock data from the Yahoo API or download some governmental climate data from some government website, or maybe one of your colleagues will give you some printout from Google Analytics that also has timestamps, right? And you want to get it into Python so you can work with it. So here's an example of something you might get. You might have somebody hand you a text file, and it's got something like this, which is not actually how this looks. So let's actually look at the text file. Oh, it is how it looks. My bad. So you've got 1950 tab separated 1 and then a value, 1950 tab separated 2 and a value. What kind of data do you think this is? Go a bit further. We've got 1950 all the way down, and we got 1 to 12. So what is that? It's monthly data, right? So sure, I can read this in and then maybe write some like row by row parsing to turn this into some PD dot period because it's a monthly data. I want interval. But I'd rather not have to do that, right? I'd rather just read it in properly to begin with. So the naive way, I might just read it and get something like this. I don't even know my column names. And maybe if I'm lazy, I'll just do it this way originally. 1951, 2, etc. And especially if I look at least 12 of these or 13, I'll figure out that it's the monthly data. And then I'll say, you know, I should really do this a little smarter, have a better script, especially if I'm going to do this more. Let's look at the read FWF docs. In particular, I'm interested in some of the things we can infer, and this one is one that jumps out at me, something like infer date time format, right? So just like Pandas has a beautiful library for dealing with time, it also extends that to reading and writing data in common data formats. So let's think about how we can modify. We can pass in, for example, a parse dates parameter, which will tell it which columns to use, and then we can actually say, why don't you go ahead and figure out that format for me? So let's try that, and then take a look at what we've got. And now we've actually got dates. If we look at the index, we've got a date time index. And then I can maybe give it some names so it looks a little better, and I've got a month and a value. Now that I've got a month and a value in an index that is time-based, I can actually find out some useful information, right? Assuming I got this and I don't even know what I've got, I can find out quickly what my min and max are, right? So get an idea of what time span I'm looking at for this data. I can Also, thinking about it, realize, well, I don't really want a timestamp, right? Because this data is not actually like at this second I took this value. It's actually a monthly average of some sort. So I'm going to convert it to a period. Remember, we've got date times and we've got periods. This feels much more like an interval to me, right? Climate data. What was the particle count for this month versus that month? So I'm going to convert it to a period. And if I do that, this looks much more sensible, right? And the way I can tell very quickly that it's done a period is it's not even bothering to include a date, right? If it puts that date in, I'm going to think, oh, it must be using that. But if it's only giving me 1950-01, 1950-02, that's telling me it's a monthly period. It's not the 1st of January 1950, it's just January 1950. So there we've got that representation. With reading in dates with a pd.read function, you usually have several time-related parameters, and sometimes the inference can be faster. Sometimes passing it a parameter string can be faster. With this file I'm using, it's really small, it doesn't matter, but if you ever have like a few 100,000 rows or a few million rows, some mega data file, you probably are going to want to be a bit thoughtful about how you ask it to parse the dates, because parsing dates is not necessarily that fast. So I've got a few examples here, right? You can give it parse dates and a date parser, like this. So if we give it both the columns to parse and also a date parser, which tells it what kind of string it's expecting. Let's see, the best of 3, 21.5 milliseconds per loop seems okay. In this second option, what's different? I'm still giving it the parse dates column. It would be kind of dysfunctional not to, right? I don't want it to always assume 1950 is a year. But I am not giving it a date parser. I'm just going to have it figure it out on its own now. And here, this actually cuts down, right? So sometimes you might think you're being helpful, but maybe you haven't expressed something that helpfully, right? So in this case, I thought, oh, I'm going to be so nice. I'm going to make this really efficient by providing a date parser, but there must be something about the way I did it that's really inefficient versus just the way that Pandas already has in the background. So that's one thing to be aware of, is your custom solution might not work so well. In this last case, I'm going to just explicitly ask it to infer the date-time format. Let's look at what that does. And that's about 7.7. So in the background, that might actually just be the same as the one above, or it might not. The point is, try a few things out with your data, find out what's fastest. You can also, let's say you've made the mistake of already reading the data in and not parsing it as you did it, or let's say you just had it in a pickle or something, but you don't have things labeled as timestamps. You do have the information. You can actually have a data frame that has columns with the separate components of the date and easily combine them. So let's say we have a data frame that has a day, hour, month, and year column. Sure, you could write your own custom function to combine them, but actually it's pretty straightforward to just do a pd.datetime on that data frame, and it will intuitively figure out how to put them together, right? You have to use proper names for your columns, but once you give it that, it will look at the data you give it, and it will convert it to the appropriate values. Now, what do you notice here? If I happen to have added a column that's not very helpful, that throws the whole thing off. So that's also good to be aware of. Okay. And finally, truncating, really easy to do. Let's say you have a time series like this one, right, going from July 2015 up until April 2016. Let's say I don't actually want it all, right? I want to get rid of things before 10/31/2015 and after 12/31/2015. That's super easy to do. And it preserves frequency, right? So there's a lot of functionality in Pandas where you can truncate, index, and you will keep that frequency bit, which is very useful. You can truncate in a way that does not preserve frequency, and you'll see that then you lose your frequency parameter, and you can't easily get it back, right? You would have to reset your index. That's because there isn't any frequency, right? If I'm going from August to January to February, there isn't an obvious way to have frequency. That's why Pandas doesn't do it. Pandas will try to preserve frequency whenever it can, though. So if you see here, I'm indexing in a regular way, right? I'm going to take every other value from my original series. In this case, it is keeping the frequency. It's bi-monthly. So Pandas will bend over backwards to try to make your date data make sense. Okay. So that's sort of working with times and working with strings that talk about times. Now we're going to progress into thinking a bit about how you're going to analyze time series data or how you're going to label it. Very common analysis tasks. So often what you want to do is you want to have a time series and you want it at a particular frequency, but you don't have it at that frequency. That's called resampling. And usually you're going to do this because you want to match it to existing data or because you just want to think about things in a certain way, right? Maybe you got data that's time-stamped every minute, but you only care about every 60 minutes or every day. Or maybe it's the other way, right? Maybe you have sort of an irregular time series of some length, right? You grabbed data when you could, and from that you'd like to have a more regular series, right? Don't sort of tell me all the time, just give me that hourly snapshot, even if that's not how you collected the data. So if you want to do that, that's called resampling, and we're going to take a look at an example where you would do that. Let's start with just a time series I'm generating here. So we start with January 1st, 2011, and we are sampling every hour, randomly picked 72 periods, and these values here are just, random values 0 through whatever. Let's say, though, that I'd actually really like to think about this data not hourly, but every 45 minutes. I'm going to use the asFreq class method. Go ahead and try this out. I'm going to try every 45 minutes, and I'm going to try a forward fill method. Before I press enter, or before you press enter, I'd recommend thinking about what do you think that means, forward fill. Well, let's think about what our data looks like, right? We're starting with hourly data. We're converting it to every 45-minute type data. So instead of this series, right, of Jan 1st at midnight, Jan 1st at 1 a.m., Jan 1st at 2 a.m., I'm going to have a new series that looks different in two ways. It's both under-inclusive and over-inclusive in the sense that some of my data points will just be gone. For example, if I start at midnight, my next data point is 12:45, right? So I have midnight, which I had originally, but now I have a new time, 12:45. Let's go 45 minutes in advance. 12:45 plus 45, what does that get me? 1:30. That means I have dropped 1 a.m. So I will both have new data points and I will be missing old data points. I have to think about how I'm going to fill in the values, right? So if I drop data, that's not a conceptual problem. It's just gone, right? I dropped the data, who cares? But if I'm adding a new point, right, a new index, what do I pick the value for that index? Well, there's lots of ways to do it. One basic way is called forward fill. So what do you think that means? Think about it, forward fill. Going forward in time, what's going to happen? So my 1 a.m. or my 12 a.m. is 0. What's my 12:45 going to be? Right, I'm going to carry it forward. That's the forward fill. So let's take a look at that. If we look at it, like we were saying, at 12 a.m. I've got 0. At 12:45 I've got 0. I skipped that 1 a.m., but at my next data point in my new series, 1:30, that 1 a.m. actually has influence, right? Because this 1 a.m. with a value of 1 has now forward filled the 1:30. Right? So even when I drop those data points as I'm resampling, the value and the information there is carried forward to some extent. Now, the opposite of forward fill would be a backward fill, right? That's my B fill. So let's go ahead and try out the B fill option. What's that going to look like? Yeah, the 1's going to be in the 12:45, right? That what's going to happen is how we pick the values changes, right? When I'm at a new data point that didn't exist in the original time-wise, instead of looking one direction, I'm going to look the other direction to figure out, right? So now that it's backfill, if I'm at that 12:45 a.m. point in time, instead of looking for what came before, I'm going to look at what came after to fill. And this is the sort of place where that domain knowledge matters, right? If I'm thinking what's the sensible way to do this, it probably depends on sort of what the people who are consuming my data want to know, how the process works, right? Whether it makes sense to backfill or forward fill. What if neither of these makes sense, though? Right? You could also imagine a case where someone says, well, I don't actually want to see fake or imputed data. I just want to know what the value was if you had it, and if you didn't have it, I just want to know that you didn't have it. Well, you have that option too. So if we were to just have the method of none, what do we think will look like now? There we go. So like the real values where I actually knew at that time I'm indicating what the measurement was, I will retain the measurement, right? So I actually took that measurement at 12 a.m. I actually took that measurement at 3 a.m. But on the other hand, The fake data points where I don't have an exact measurement, I will have that indication. When might this be useful? Maybe you want to join with some other time-based data, but you want to know either the actual value or that you had nothing, right? So all of these are legitimate ways to fill your resampled time series depending on what you want to know. I don't know. Yes. Yes. You can make it interpolate, and I think we will talk about that in a little bit, actually. And there's also, of course, different ways to interpolate, right? You can do a linear interpolation, you can do a polynomial interpolation, etc. Okay. So what does the above code do to the size and content of your data frame? Well, we already saw this, right? You get more data points, and in particular, you'll want to think about the fact that you are actually making a larger series if you're upsampling, right? If you're going to a higher frequency, you will have more data points. You can also do the opposite, though, right? You can go to a lower frequency. Okay. So that is the .asFreq method. We can also look at other options we've got here, right? We can normalize. We can also have a fill value. Good to be aware of. Okay. Let's say I want to go less frequent rather than more frequent, right? So I had hourly, but maybe now I want every 3 hours. So let me just print out that TS again so we remember what that looks like. So here's our original time series. I now want to sample it only every 3 hours. And here I've got 3, 6, 9, 12, 15, etc. 3 a.m., 6 a.m., 9 a.m., a couple things to notice. One is that it started by including the time on the later end rather than the earlier end. That's the left versus the right. That's parameterized. You can easily change it so that it would be 12 a.m., 3 a.m., picking the leftmost option. Another thing here is I'm not missing data, right, because I'm strictly taking a subset of my original data points. But it's not super interesting in the sense of this does just lose information, right? Instead of knowing that I had 0, 1, 2, 3, I've just got the 3, 6, 9. And maybe that's what you want, but maybe sometimes you'd actually like to do something different, which might be what? You might want to average, right? You might say, well, since I'm dropping down to every 3 hours, I actually want some summary statistic for that 3 hours. Maybe the average. Maybe I want to know the min for every 3 hours, the max for every 3 hours, the sum. You name it, you can do it. So what you're going to do there is you're going to do something called resampling. It's the exact same idea, except that now you can do a summary statistic rather than just grabbing some arbitrary value. So asFreq will always just pick one of those points, forward fill or backfill. If you want to do something fancier, you're going to go with a resample. So for example, here I'm going to resample every 2 hours. For the label, right, that's picking whether I start at midnight or 3 a.m., for example, in the case, right? Do I pick the left value, meaning the earlier in time value, or the right value, meaning the later in time value for my label on this statistic, since I'm going to be dropping points? So if I do this, I take every 2 hours and I take a mean. We can see this here, right? So we've got 0.5, 2.5. Now I'm taking a mean. I have a way of sort of describing the whole interval as I am downsampling to a lower frequency. If I want to get an idea of some of my options here, you can see that resample gives me a lot more options than asFreq, right? I can have a limit, I can have a label. I still can have a fill method if I want. I can pick an axis. It's just a much more flexible function. And what's particularly useful is that we can resample even to even out irregular time series, right? So if for some reason you have some time series that wasn't sampled on the hour, right? Maybe you had 1 a.m., and then you had 3:15, and then you had 7:27, but you would actually like to present it in a more regular format, you can also do that. So if we look at my irregular time series here, you can see I did 11 p.m. on the first and then 2 p.m. on the second. If I want to just resample that, I can do an asFreq, and that will get me down to what I want. Okay, so why didn't that work, what I did? I took my irregular time series, I sampled it as frequency daily, and it just gave me back January 1st, 2011. It's not really what I wanted. And I certainly have other days here, right? I thought I was all done. What went wrong? Pandas is terrible. This is a wash. I need a new library. No, right? It's out of order, so that can also really mess you up. One thing you want to be aware of with Pandas is it does expect your data to be in a sensible order when you're dealing with time. So if you just go ahead and do a sort index like this, and then you try that daily method again, you will now find that you have sampled and it has behaved as expected. I can do a backfill. I can also say do a resample and take a mean. So it's a nice, easy way to clean up your irregular time series. Just because they're irregular, though, that's not enough. They do have to at least be in order. Okay, so a couple of exercises to try and digest this stuff. Let's go ahead and take 5 minutes. Let's also just call this a 5-minute break. If anyone's been waiting to run out and get a drink of water or use the bathroom, please take advantage. And we will reconvene at 2:31. let's talk a bit about resampling. So what if you want to go to a higher frequency, upsample, right? Like our first example where you're actually adding new data points, times that you didn't originally measure, and you don't want to backfill or forward fill. What's the way to do that? So method equals none, right? So if we were to do an asFreq, for example, and we're, say, upsampling from hourly to every 45 minutes, if we just pass in method equals none, those values where we didn't actually take a measurement will come back as nans so that we know we didn't actually take a measurement. Real world question, why might you actually want to do that? What's a use case where you might want to do that? Nobody has a use case from work or something? So I can give you one. So we look at when people with diabetes, say, take carbs in. We might have this idea that people eat every 3 hours. So we say, well, let's sample every 3 hours from our every 6-hour data that we originally collected. And so those people who happen to have every 3 hours because they put in extra data points will get that data, and those that don't will have the nans, right? So if you, say, have people with different levels of data density, where sometimes they'll have it and sometimes they don't, that's one use case. Another use case is maybe where you're doing a join with another data source. So for example, I have climate data, I'm collecting particle counts in Portland, and I'm just treating Portland as Portland. I don't actually care about neighborhood. And one sensor went off every 30 minutes, and another sensor went off every 17 minutes. And so if I start sampling every 17 minutes or something like that, if the one sensor was firing off, I'm good, right? So as long as that sensor was firing, I'm good. If it wasn't, I'll put in a nan. So when you have, say, parallel sources of data, that's another time when this might be useful to put in a none. Okay. What's the difference as far as you can see between resample and asFreq? So we started with asFreq, which just upsamples and downsamples, and it just forward fills or backfills, and it's pretty plain vanilla. And then we moved to resample when we wanted to start doing summary statistics of some kind, right? So a resample, a dot resample, is almost like a dot group by in SQL. It gives you a resample object, which you can then sort of pass down your pipeline to do things like take the mean, take the median, take the max, take the min. So if you just want to convert your series to a different frequency, just go with asFreq. That's more direct. But on the other hand, if you want to somehow, especially when you're downsampling, right, if you're going from, say, hourly data to data that comes every 5 hours, and you want to have a way of using all of the data, right, rather than just grabbing the point in the time series that corresponds to that time period, you will use resample, right? And then you can do something that uses all the data you used during that time period. Okay, what if I want to forward fill, right? So I'm going to upsample. I'm going to go from a lower frequency to a higher frequency, but now I want to forward fill only a few days or only a few minutes or whatever, like only a few periods. So what if I have this idea, let's say with the particle data, let's say I am sampling. Let's say I am sampling every 7 days. Now let's do 6 days. That's easier. Every 6 days. And now I want to upsample and pretend that I was sampling every 3 days for some down the line pipeline issue. So now I'm going to upsample to let's say every day, from 6 days to every day. And I have the domain knowledge that the particle count that I take on one day is generally accurate for, say, 2 days. So it's not generally accurate for 6 days, but it is accurate for 2 days. That means that when I go from my every 6-day measurements to my daily measurements, it is sort of scientifically valid to fill in part of my time series, right? So if I measured every 6 days, I can actually take that day, like day 1, and carry it forward 2 days, but I can't carry it forward for the full 5 days I need to fill in that will be blank. How would I do that? Well, let's say I don't know for some bizarre scientific reason that it can go backwards in time. It can only go forwards, for my fairy tale example, right? But I would certainly want to think about that in the real world, right? And that at some point when you're backfilling and forward filling, then you might as well just interpolate. But if I have it only going in one direction, what might I do? So one thing is just a fill NA, right? So just standard pandas methods that aren't even time related, right? So I could, For example, do an as frequency, bring it up to my faster frequency. Start with a method of none, so originally everything is a nan. Then once I have all my nans, Pandas gives me all sorts of ways to just deal with them, even apart from time functionality. So I can do a forward fill on my nans and put in my limit there. And that's an example where if you have that domain knowledge, you can do a partial forward fill. And then again, with the resample, just to hammer in number 2, a resample or a resampler object is just like a group by. It's just a way to do these sort of aggregate statistics over larger periods of time as you are downsampling. Okay. I'm not asking for questions because I'm going to just assume people are shouting them out when you have them. Is that fair, or do we want a separate question? No. Okay, so keep shouting out the questions as they occur to you. Moving right along to moving window functions. Okay, so a couple things you want to just be aware of if you really haven't dealt with time functions before when you're looking at time series. There's a couple of things we do with time series, very standard exploration. One is a lag function, right, where you just want to sort of move your function back or forward in time. And when you do this, it's usually because you're thinking about the difference, right? So when I talk about a lag function, all I'm doing is taking my time series, and I am literally just kicking it back one period. I am taking the whole time series and just shifting it back 1 unit in time. And I'm going to do that just because I'm going to want to look at the difference between them. So when people talk about a lag time series, that's what they're talking about. You can also lag for any number of periods you want. So maybe you won't lag 1 period. Maybe you'll lag 10 periods or 12 periods. That partly depends on your domain knowledge and what you're trying to figure out. Another common way of exploring time series data is window functions, right? And what you're doing here is you are basically trying to smooth out your information that you're getting from that time series. And there are 2 common sorts of windows to use. One is called a rolling window. This is the one you are probably more familiar with, that you have seen more. You can almost sort of think of this as smoothing, right? It's not quite the same as smoothing, but it's similar to smoothing. So let's say, looking at this left-hand side, I've got this time series, this jagged data. You can see it. It sort of jumps around, right? All natural data will jump around. You have measurement error. You just have normal statistical variations. But I really want a smooth line, right? Because I'm a human being. I like to think that there's some true mean or some true behavior that is in that data. So one way you can do that is you can sort of have a window, and the window moves over a few points at a time, computes some way of combining that data, usually it's some kind of weighted mean, and assigns a point, right, for time. What do you notice, though, about the rolling window function? It's not just smoothing, right? If you think about it, look at where the dips in my real data are, the dips here, versus in my rolling window smoothing functionality, it's here. So what is the other thing about a rolling window versus just smoothing, or, yes? Yeah, there's going to be a lag, right? Your rolling window will slowly respond to the changes, but it's always going to be sort of behind your data, not at the same point as your data. That would really be more of an estimation of your time series. Expanding window, can anyone sort of guess from this graphic what an expanding window is? Let's think about it. So it's some kind of cumulative summation, right? Rather than a moving summation, in this case, it just keeps using the information as you get it. So with a rolling window, if you use a rolling window, what you're basically saying is the valuable information is the at a particular point is the information that's near that point in time and really just behind that point in time, right? Because you don't want to usually use the future. So you're just sort of moving forward computing, right? And this is like, for example, the stock market. If you were to think about it, you don't know what the stock market will trade in the future. So the best you can do is sort of maybe take a 5-day average and move that 5-day average forward, or a 5 microsecond average, depending on what kind of stocks you're looking at. On the other hand, you might have a process where you don't actually think it's moving around, or for some reason, you have domain knowledge to believe that all information is relevant to now. So there could be some kind of data I have measured for a very long time, years or eons or nanoseconds, depending on your field, where you believe that the first measurement, even though it's more distant in time, is somehow still interesting to tell me what the measurement is now. So that's when you would use an expanding window. Does anyone use expanding windows in their work, or can you think of an application?
Yeah, if you've got a stochastic experiment and you get lots of observations of the mean, you think the cumulative mean is your best estimate of where you are.
Mm-hmm.
And gives you that sense of the convergence.
Mm-hmm. So if you have something, for example, that's a time series but might actually be measuring a static property, right, which often happens, that is one case where you have an expanding window. One case that comes to mind that's kind of controversial is political polling. So some experiments indicate that people don't actually change who they vote for. They might start becoming more honest or open with pollsters, but they tend to have the same opinion maybe even a year before an election. So you could argue that rather than a rolling window, which is what most pollsters do use, that you actually want an expanding window where you can view sort of the responses to the poll over time as really just giving you that mean that was maybe true a year ago, right? Because most people don't change their voting identities. So anything where you think that the information from a long time ago was just as valuable. Okay. So why we use a rolling window function? Well, we talked about it a bit. Usually people are looking to smooth out data. We talked about already how what's a little funky here is your smoothing with your rolling window is always going to be a little bit behind. What's the difference between these two? They're both rolling windows. The window size, right? So that's the other interesting thing to think about when you look at rolling windows is you can make your rolling window really narrow, like this one in the bottom. What's the advantage of that? Yeah, so it's closer to your actual time series, and there's a tension here, right? Because you'd say if you want your actual time series, just use your time series, right? Why smooth it at all? Why do you still smooth it, even if you mostly want your time series? Yeah, so we want to get rid of noise, right? Especially if we believe our noise is some sort of IID Gaussian, we just want to sort of delete that, but otherwise have our time series. Something with a fairly narrow window, just sufficient to get rid of that noise, can be nice. On the other hand, why might I want to use something more like the smooth curve above? Yeah, so like if you are more interested in long-term trends, right? So if we imagine again that this is, say, financial data, maybe I'm the kind of investor, I'm getting ready for my retirement in a few decades. I don't want to respond to these shocks, right? I actually, maybe even psychologically, I don't want to look at them, right? When I look at my retirement portfolio, I just want to see this blue line. I don't want the stress of looking at that green line, right? And I have certainly had even jobs where I have noticed that people in upper-level management also didn't want the stress, right? And they preferred when the analytics people sent them up like a really long rolling window rather than a shorter one, and everyone was happy. So when you're thinking about your window size, it's both domain knowledge and also sort of what you want, both psychologically or sort of like what your purpose is with that rolling window. So with that rolling window stuff, let's go ahead and look at our notebook and see how we can do it. Where's my notebook? Okay, so we are looking at our moving window functions. First thing we want to do is learn how we can compute a lagged time series. So if we have a time series, we can just do the lag by making it ts.shift. And let's see what happens if we do that. So my first time series I set up as a daily frequency from July 1st, 2016. My lagged time series, I just did ts.shift. Let's see what that gives us. Well, it starts on the same day, but now it gives me a nan for my first day, right? Why is that? Because I shifted everything back, which means for my first day, I don't actually know what that value was, right? There isn't a value. There's nothing before that to shift up. So that one's a nan. What else does that mean? What do we think the tail is going to look like? The tail is July 20th. What about my original time series? Also July 20th. So what do you notice here? I just kicked off a time point. I just lost it. Something to be aware of, right? So it really does just shift it, but preserves your initial indices, which can be nice if you don't want to start adding indices, right? You really just want to compute the lag. I do this usually because I want to be able to do a difference, right? One way I can do a difference is I can just subtract it out like this. You can also, though, instead of computing it yourself, there's ts.diff, which will actually just give you the exact same time series. So I don't have to explicitly do the lag myself, although it's good to understand where it came from. What if I don't want to do one period? Right, this assumes I just want to shift by one period, but there are legit reasons to do more than one period. Let's say I have yearly data, and I want to look at year-over-year trends. I'm not going to shift by one, right? Or if I have monthly data and I want year-over-year trends. If I shift by one, that'll just give me month-over-month trends. How would I do year-over-year? Shift by 12, right? And actually both of these, you can just pass in a different number, and it will shift according to what you pass in, right? So if I could put a 2 here and I'm going to shift 2 periods. I can also put a -2 in and shift the other way in time. So it handles both positive and negative. Very handy to know. Okay. So Pandas does it to you. So quick question, how do I shift my time series into the future instead of into the past? Just go ahead and type it out for yourself. So I just did it here. What's different in my code? Just this one line? I shifted -1, right? So instead of leaving it blank, which is just 1 it defaults to, I do -1. And you can actually see here, look, my red, which is my lagged, except now it's sort of future lagged time series, has just been moved to the left by 1. So very, very flexible. So that's my lags. Window functions. Let's look at our window functions. We were just talking about how helpful they are, how you want to think carefully about how you do them. How am I going to do a window function? Well, let's start with a data frame and take a look at the data frame I made. What have we got here? We've just got some randomly generated numbers, and I'm correlating them to dates. Notice I'm not using periods. It's not important, but you just want to be aware of what you're working with. So here we're actually looking at timestamps as indices. I want to do now a rolling. If I do a rolling, so I do df.rolling, a nice class method there, I just get a rolling. Well, what's that? Why do I just get a rolling? Haven't done anything yet with it, right? I've just told this data frame, prepare, like, please aggregate with a window of 20 periods at a time, but I haven't actually told it how to aggregate, right? It's like doing a group by and then not giving it an operation to do on the group. So you get these rolling objects. Let's actually do something with it. So I can take my R and maybe look at the mean. And here we go, right? There's my nice moving average looking at the mean. And you'll notice I've got some points here on the left where I don't have anything. Why is that? Yeah, I don't have my 20 observations, right? So it's not going, if I say a window of 20, it doesn't mean at most 20. It means exactly 20. So until I get to 20, I don't have any. That's something to keep in mind. For example, if you have a really short time series, you might want a really large window, but you might not be able to afford it, right? Because then you might end up only having a trend line for some very small subset of your data. Okay. What if I want to look at the min instead? I can do that too, right? I can do any sort of function. I can put it in. I can put in a custom lambda function if I want. One interesting thing here, look, my rolling mean is just sort of this kind of jagged, right? Because it's still only an average of 20 points. They're still fluctuating enough that I see jumps, but it's fairly smooth, right? And I can certainly smooth it more by just making my window a lot bigger, right? So for example, the bigger my window gets, the smoother my average is going to get because each data point is less important, right? On the other hand, there are certain functions I can do like this. And this is not really giving me a smooth function at all, right? So here I'm doing a rolling window and selecting the min in that window. So why does this look so awful, or does it? It's accurate, right? So we're used to thinking of window functions as something where you just do a rolling mean to smooth, but you also might just want other information that will jump around, right? So let's say I want to know in diabetes terms, like what was the lowest blood sugar this person has had recently, right, with this 20 or 50 period look back. And that's actually just accurately describing, right? So if I pick a function that's not going to have a remotely smooth transition, there's nothing wrong with that. It's different kind of information. Okay. So let's try out a couple of others. Just play around on your own with rag, rapply, rcount, r.max. See if you find anything interesting. Just take a minute. So for my rolling object, I applied the quantile function at the 30th percentile, and this is sort of an interesting way to get a happy medium between something that jumps around a lot and something that's really smooth and seems like no individual data point contributes. Anyone see anything they want to share? Anything interesting? Okay, not so much. So just good to be aware of the rolling function, just like a group by, whatever statistic you want to do to summarize. Okay, what about a custom function? What if I have some really weird way that I want to aggregate my data or get information about my data? See if you can formulate a way to do your own custom summary. You're going to get in a list of 20 values or 50 values or whatever you set your window size as. What are you going to do with it? Bless you. So I've got a fairly dysfunctional example here of what you might want to do. df.rolling. Let's say I've got a window of size 10. I'm going to just do an apply and stick my lambda right in. And I've got a bunch of nons to start with. Why? Those are just my, again, at the beginning, right? If my window is looking backwards, I need to get to 10 before I have anything. So let's just go ahead and look at the next set, and I've just got numbers that describe the second value in that window divided by the third value in that window. I don't know why you'd want to do that, but if you wanted to, one dysfunctional way to do it is your rolling function. I would hope you wouldn't do this though, right? Because then you don't really need a rolling window to do this, right? Let's see another example. Here I'm just plotting it, right? And again, you can see it's fairly dysfunctional, but it just shows I can do anything I want. I'm just going to get this ordered list in, so you get that ordering information, and you can use it however you want. What would be maybe a less dysfunctional thing I'd want to do that might be custom? I could do custom weights, for example, right? I might have some weird nonlinear or non-functional form type of weighting I want to do. So I don't want to do an exponentially weighted moving average. I have my own custom weighting, which might be informed by domain knowledge. So I want to put those weights in, although there are other ways to do it. I might want to only take every other value within my window, but just do that with my Lambda rather than looking for some way with the Pandas API. I might want to, if the values are high, weigh them one way, and if they're low, weigh them another way, right? Again, maybe informed by domain knowledge. The point is, in your domain, no matter how kooky it is, if Pandas doesn't handle it, your Lambda function certainly can. Okay. Expanding windows, less common, but you do want to know how to do them. Instead of a rolling, you just have a dot expanding, and you'll notice it does let you set a min number of periods. So for example, if you don't want to start with just one, if you want to have still some minimum window size, you can easily set that. In this case, I did just set a min period of 1, so I have values for each. Yes?
So with rolling windows, of course, the one issue is set window before you start the data set. It's a little less measures, but you're doing so 1 day, 2 days, 3 days, you do 20, so you still fill in some type of important part of the data.
So the question, if I understand it, is there a way to have a rolling window but not have NaN, so maybe have an expanding window and then a rolling window? So in that case, I think I would probably do like a fill NA, so I'd probably do my rolling window first and then backtrack and do a fill NA with an expanding window, would be one way to do it. You could also, for example, say, well, once I get to 20, I want to use a rolling window of 20 and then backfill with smaller and smaller rolling windows. That's another way to do it. It would depend on your domain needs. Cool. Okay, so let's try out a couple of things here. First question, how can you perform an exponentially weighted moving average? These are really common in a lot of applications, so it's good to go through the docs and find that. Secondly, think a bit about how and when you'd use an expanding versus a rolling window. Third, try to write a custom function to replace the quantile function for a moving average and use it the way you would use a custom lambda, just to make sure you remember how to do that. And fourth, think about how would you compute more than one aggregation function on a moving window. So let's say you wanted to take both the mean and the median and maybe the sum. How would you do that all in one line of code to keep your code nice and simple and clean? So go ahead and work on those. I think this is also when they roll out the goodies at 3 o'clock. So if people's stomachs are growling and stuff, maybe we'll take another break. That will coincide with working on these exercises. So let's reconvene at 3:09 to talk about the exercises, but also go grab some snacks. Mm-hmm. Let's see, is this on now? Back up. As a reminder, we had 4 questions we wanted to take a look at during the break. The first one is, how do you perform an exponentially weighted moving average? Right. You could code it up as a lambda function. You probably don't want to because that seems like a lot of work. This is something that is common in a lot of disciplines. And also for those who haven't seen an exponentially weighted moving average, it looks something like this. So what do you notice about this shape? It's not linear. So if you use this, what are you saying about your data? When you're weighting, you're not weighting all points in your window evenly. What are you doing? More recent points are more important, right? So you can almost think about this as a little bit like the divide between the expanding window and the moving window, right? The expanding window says all points are interesting and I want to keep including data. The moving window says I only care about recency. You are applying this with a moving window, but you are saying even within my window, I care about recency. I want to include some things, but weigh them less. They're less informative, right? It happened too long ago. So I mostly want to ignore it, right? This point out here, maybe 20 days ago, I mostly want to ignore it, versus the data point I just collected, that's going to be the most valuable. So you can do that with an exponentially weighted moving average. It's the most common way across many disciplines. In Pandas, this is one way that you can do it, is with the .ewm. And you can take a look here. It will give you a very nice, lagged, smoothed version of your time series. Just like with your moving window, it's got a bunch of parameters to adjust, so you can sort of think about the half-life that you want, think about how steeply you want your weights to drop off, and you can sort of play around with that. Again, depends on your domain knowledge, depends on what you're looking to get out of it. Okay. Second question, we talked about this a bit, but when would you use an expanding window versus a rolling window? The default tends to be rolling window, so it's more like why would you use an expanding window is another way to frame that question. Right, so when even data really far in the past is informative, such as when, even though it's a time series, it's actually measuring, say, some static information, right? So it could be that your information is getting better rather than that the situation is changing. And when you have time series, you often want to think about that. Is it the underlying process that is changing, or is it only my measurement that is changing? If it's my measurement that's changing, an expanding window is probably more interesting, versus if I think my underlying measurement and my actual situation are both responding. Okay. What about writing a custom function to replace .quantile 0.5 for a moving average? How would I do that? So one way to do it is I just implemented one example here. If I want the 50th percentile, I can just sort and take the middle one. The point is really that you just want to remember you can use a lambda, right? So you can come up with any summary statistic you want. And then finally, what if you wanted to compute more than one aggregation function at a time with your rolling window? Well, you can do that df.rolling. It's just like a df.groupby for people who are familiar with Pandas again. I can do a .ag and have lots of methods that I want to compute, right? I can do a sum and a mean for all of my columns at the same time. I can also stick in custom lambda functions as part of my aggregation. Okay, so those are moving windows. Okay, so now we're going to start talking about things that are related to trying to make predictions about time series. And we're going to start by thinking about and talking about self-correlation. So time series data, in my opinion, is always really interesting because even a time series that has only one value, right? I'm only measuring one thing, but I'm measuring it over time, is actually really interesting because there can be a lot of internal structure. For example, if you have something that has some sort of yearly pattern, you're going to see every 12 measurements, if you're measuring monthly, every month, you see some kind of repetition. So it's not just some boring, like I only get one number, so I only have one kind of relationship. I actually can have infinite relationships, right? Because I can look at how every point relates to all the other points in time. I can look for periodicity. And that is what self-correlation is about. So there's 2 functions we use to look at the structure of time series. One is the autocorrelation function. This is used to help identify possible structure in time series data. It gives a sense of how different points in time relate to each other in a way explained by temporal distance. So when you're thinking about autocorrelation, you aren't necessarily thinking about data that is segmented according to evenly spaced points in time. If you're looking at autocorrelation for an irregular time series, that doesn't necessarily make sense, right? So if I have my first data point, and then I have 2 days, and then I have 17 days, right? It doesn't really make sense to be looking at those measurements and looking for structure. I am assuming that these are regularly spaced data points. And if I do that, I might want to think about, let's say I have daily data. Well, I would assume that Mondays tend to be similar. So I might look at how every Monday relates, right? So if one Monday value is 10, maybe the next Monday's value is more likely to be 10 than to be some other value, right? Maybe they're highly correlated. Or maybe they're negatively correlated, right? So maybe there's some inverse weekly cycle, right, where one week, if it's high, the next week it's going to be low, then it'll be high. I can have some sort of negative correlation. So what you can see here is on the top, you see a time series that if you look at this, to be perfectly honest, I would look at that and say, I don't know if I see any structure. Like maybe this is just some random, people measured noise on the subway and it had nothing to do with anything. But then if I look at the autocorrelation function, I can actually see that there's some very high correlations at certain periods. So the first point will always be 1, because that's always going to just be like a delta of 0. How does a point correlate with itself? If that is not 1, there is definitely a problem in your code, or there is a NaN somewhere. So that should always be 1, right? How does a point correlate with itself? When I go to the next point, what I am saying is I am tallying up the correlation for every point in time. I am looking at the point in time lagged 1 behind it, and I am calculating that correlation. So say you have a time series that is 10 long. When I'm looking at the autocorrelation function of a lag of 1, how many correlations am I looking at? Well, I'm looking at from 1 to 2, from 2 to 3, from 3 to 4, from 4 to 5, from 5 to 6, from 6 to 7, from 7 to 8, from 8 to 9, from 9 to 10, right? So even though I've just got this one string of numbers, each of those pairs is giving me the lag 1 autocorrelation value. What if I'm looking at the lag 2 autocorrelation value? From day 1, I'm saying, well, how does day 1 relate to day 3? What's the next day I try? Do I go to day 3 and look at how it correlates to day 5? No. Where do I go? Day 2, right? So it's day 1 to day 3, day 2 to day 4, day 3 to day 5, day 4 to day 6, right? So every point counts. What if I only have 10 and I'm doing the lag of 9? I only get one observation, right? So intrinsically, I am limited to the amount of time I have observed. That's the furthest out I can go. And let's say I only have 10 and I want to look at lag 9. Do I really want to? No, right? For a couple of reasons, all of which would be saying the same thing in many different ways. If I've only got one observation, what's my uncertainty? I have no idea, right? I have no way of knowing what any sort of metric of what the variation in that autocorrelation is. I can't have any sort of confidence interval. I have no idea. So you want to pick some sensible limit to how far out you're looking, because the larger your lag you're looking at for your autocorrelation, the fewer data points you have. Okay, so this is just a great example of how you might have real order when you think you have chaos. That's the autocorrelation function. Can you think of a problem, or at least a wrinkle, with the autocorrelation function? Let's say that I have weekly data. I just think about humans and they work in weeks. And people tend to have high stress levels on Mondays. High stress levels on Mondays. So I might see, and every other day it's sort of random and it washes out, but I might see a really high autocorrelation at 7 days, right? Because all those Mondays anyway, right? The Tuesday, Wednesday, etc., they might give low, but still on the Mondays I'm getting a really strong signal, so that'll give me a high autocorrelation for 7 days. But what else will I see? 14 days, right? I'll have a really high autocorrelation for 14 days. And what else? 21 days and 28 days and 7 times a million, if I have enough data, I will also see a really high correlation. And this is some problem you will have with periodic data, right? You will see that it will just spike. But that's not actually meaningful, right? What's actually happening is what? Why do I have correlations 14 days? Well, it's really because I have the correlation 7 days, right? It's just like harmonics. It's just multiples. So what am I going to do about that? I really only want the true correlation, right? So I want the shorter time period. I'm going to use something called the partial autocorrelation function. So what the partial autocorrelation function does is it gives the partial correlation of a time series with its own lagged values, controlling for the values of time series at all shorter lags. So that means that if a correlation can be explained by a shorter time period, it's not allowed to take that same correlation and sort of recycle it and give credit to that longer time period. We're going to say that the shorter time period with the correlation is the real one, the more natural one. We're going to take that out, and then we're going to see, is there any more correlation, right? Is there a 7-day effect and also a 14-day effect? And that will be, say, the true 14-day effect, because we've taken out the part that can otherwise be explained. Does that make sense? This is a bit trickier. Yes. Thank you. I like that. Okay. So that's autocorrelation and partial autocorrelation. So let's go ahead and see how we can do this with Python. We're going to now look at stats models, and in particular look at the TSA module, the time series analysis module. There's some random Yahoo stock data and a CSV. So let's look at the autocorrelation first. We're going to start with some white noise, so just generate some random white noise. This looks pretty random. To my mind, this doesn't look any different from the one that we looked at in the slides here, right? So I always say try to keep an open mind. Just because something looks like white noise, it isn't necessarily. You really want to prove out to yourself whether it has structure or not. So I'm going to use the stattools.acf, and I am going to throw my result curve, which is just noise here, into that. And I want to take a look at what my ACF looks like. Remember, 0 is just correlation with itself. So even with white noise, your 0 lag is, of course, going to be 1, right? You correlate with yourself perfectly. But after that, these dotted lines are just sort of a significance cutoff, kind of arbitrary. Again, you need to make your own decisions. But for our purposes today, it's just a standard significance cutoff. What do we see? There's really no autocorrelation, right? Out here, it does pass significance. This is the 95% confidence interval, so 1 out of 20 times I do expect a random value to pop up over my confidence interval. That's all that has happened out here. That will happen. You want to be aware of it. The shorter your time series, the more likely you are to have that sort of randomly statistical blip. But white noise doesn't give me an autocorrelation, right? And it shouldn't. What about a periodic function, though, right? So now let's look at a sine. Got a nice sine curve, and let's look at the autocorrelation there. And what do we see? It's like off the charts, right? And this is what we were already talking about, that if you have something that can be explained by a shorter time period, but you're not using your partial autocorrelation, you are going to see that sort of echoing out, right? Sort of infinitely, like you're going to still keep seeing significant correlation. Okay. So let's look at a real example. We've got our Yahoo stock info. I think this is Apple, maybe? I don't remember. If we look at an autocorrelation now for real data, what do we expect to see? Well, it depends on the domain, right? If I'm looking at human behavior versus if I'm looking at stock prices about which I know nothing versus if I'm looking at astronomical data, you want to use your domain knowledge. Otherwise, you should look at things and sort of interpret as you go, but maybe think, well, maybe I don't know what I'm talking about. So I have an ACF of stock data, and now I have this really weird thing. I've got a bunch of significant values, and then they sort of cross and they go negative significant, right? So positive correlations at short values, negative correlations at longer values. Am I like learning anything intrinsically about the stock market here? Not really. What's going on here? Well, let's go back and look at what this particular stock did. It went from a lower value to a really high value here, right, in this moment in time. I think this is over a couple of years of time. So whatever this stock was, it enjoyed this tremendous period of growth. What does that mean? That means that values that are closer together, well, they will be correlated, right, because the stock market closes and then it opens again at the next day. So days do tend to be related to each other, but it means that when days are getting further apart here, they will be negatively correlated because there was a trend, right? So it's just telling me something, not about the structure that's recurring in smaller segments, but it's telling me that overall there was a trend. Now, that's not that useful as far as thinking about correlations, right? For correlations, I'm sort of looking for things that repeat. This is an example of why I don't usually look at autocorrelations in this kind of untreated data. And in particular, what I mean is there's a trend here. We're going to soon talk about why you want to detrend your data before you try to analyze it, because these sorts of tools are not meant to be looking for trends, right? I can spot a trend just by looking at the line going up. When I'm looking at autocorrelation, I'm really looking for internal structure. So okay, so let's see an example where maybe it's a little less random, right? The stock market defies everybody. You know, if someone figures it out, they'll be a billionaire. I guess there are a few of those, but let's think about something where we have a better sense of why the data is behaving a certain way. So this is a very, very popular data set, the air passengers data set. It's count of air passengers by month for decades and decades. And we can see here some data where we can even visually identify the structure. And what we see is there seems to be some kind of yearly trend, right? We almost have the exact same curve from year to year, right? There's sort of a seasonal spike, a seasonal low. This is something where I say, I even see the structure. So for here, I would certainly expect to see some sort of internal correlation. Now, there definitely is still the problem of the trend, right? It's no different from that stock where it was going up. But there's something else, and I want to see that something else. So let's take a look at the autocorrelation function here. I see my trend, right, which is the fact that it's like a line, but I also see this recurrent structure, which is the part I care about. So that looks meaningful but worrying. What I probably want to do now is I want to detrend my data, and I'm going to do that by taking the log and also taking the difference. Why am I taking a log and a difference? I'm trying to get towards stationarity. We're going to talk about that in a second, but the idea is I want to make my time series look more like something that is relatively constant in time, the variance is constant in time, the mean is constant in time, so then I can look at why sometimes it's above the mean and why sometimes it's below the mean without having this distraction of an overall drift. So if I difference my data and take the log, I've got something where we can see the variance looks fairly stable, the mean looks fairly stable. And if I now look at the ACF, what do I see? I see something that doesn't have some crazy trend. So this is more what I'm looking for, right? Is some sort of internal constant structure that's not just superimposed by a massive spike. And I see periods. What do I, yes? The x-axis is the lag. So 0 is a lag of 0 to 0, right? So that's number with itself. 1 is the correlation between a number and the number that comes in the next period. 2 is a difference of 2, and we're counting up all the points. So here what you see, where do I see a high correlation? At 12, and at 24, and at 36. Not surprisingly, right? Because what I'm seeing is year-to-year periodicity. Now, there are problems with seasonal data as far as recurring. We'll talk about that in a bit. But what I do want to point out here is we can spot the internal structure, right? So if we didn't know how humans worked, if we didn't know about months and years, we would nonetheless be able to take this data and see, wow, it has a really high autocorrelation at 12. So there must be something important about the number 12. So that's self-correlation.
Question on the autocorrelation graph. So like for lag 1,
Mm-hmm.
is it averaging across all the possible points?
Yes. So it's averaging across them. And actually, like you can also usually put in uncertainty bands, right, where you will think about how many points you have. And of course, the bigger the lag, the fewer points you have, the wider your uncertainty bands. Yep. So that's self-correlation. Okay, so that's the first thing we want to think about, because self-correlation is part of how we do diagnostics in terms of thinking about what kind of model we want to use. The next thing we want to do is munge our data so that it looks like what we need it to look like to do an ARIMA model. So we need to do some pre-prediction munging, looking for stationarity. So to use an ARIMA model, which is one of the most powerful ways of predicting time series, one of the most inclusive ways of predicting time series, one of the most general ways of predicting time series, you need a stationary time series. Most real-world time series are not naturally stationary, right? The ones that are probably things like we talked about where you're actually measuring something that itself is fairly constant and you're really just seeing your measurements jump around. In the real world, most things are changing, right? Their variance is changing, their mean is changing, right? Stock data, airline passengers, carbon, air count, whatever it is. So you usually want to transform it, but to transform, you need to know what you're aiming for. A stationary time series has a constant mean, a constant variance, and a constant autocorrelation, right? Which is basically you're saying the value is not drifting over time, the variance / unpredictability is not drifting over time, and autocorrelation, the structure is not changing over time, right? You're saying you have a time series that behaves a certain way, and it's always going to behave that way. Not realistic in the real world, but locally it can be true. So stationarity, if you look at this though, can be tricky to decide. Of all of these plots, the only ones that are actually stationary in the sense of passing a test for stationarity are B and G. Now, I don't know about you, but I wouldn't put a lot of money on these are the stationary ones and somehow being able to say, well, it's obvious that this one isn't, or it's obvious that this one isn't. So that's just something to be aware of. When you look at data, just like when we looked at that function that has a really nice autocorrelation function, but it looks random, you can have the opposite problem, that something looks random and looks like it's stationary, but actually isn't, right? And this is where time series can get tricky, and where you have to adjust your data to fit your model as best you can. So what do you do if you don't have a stationary time series? Because undoubtedly, you will almost never really have a stationary time series. The first thing you can do is difference. So if you look at this time series on the left, that's clearly not stationary, right? You've got big jumps. You seem to also sort of have a trend, right? It seems to be trending upward. If you difference it, well, that looks pretty good, actually, right? It might still have some problems with the variance, but we have detrended it just by taking a difference. That's one very common way of dealing with non-stationary data. Your first step, just difference. You need to remove the trend and seasonal elements before forecasting. Most interesting data in the real world will show both trends and seasonality. Most models require data that shows neither of these. You need that stationary time series. So you can difference, that's one way to get rid of it. Detrending in general, right? You can also detrend by taking some kind of moving average, which we see on the left, right? You take a moving average with your window function, and you actually subtract that moving average out. That's fairly computationally taxing, right? It also means you subtracted a different value from each point. That makes me kind of uncomfortable in terms of having to explain later how I got to my model, so you can do that. It's not optimal. You can use a linear regression, as we see on the right. That's another way of doing it. The linear regression is nice because I have just the one parameter I used, right? It's like, oh, well, I just used, y equals mx plus b. I fit for my m, I fit for my b, and I applied that uniformly. So that's very tempting as far as simplicity of the model. But I'd say overall it's worse performance-wise. Why? What do you think of this detrend versus this detrend? It's still not stationary, clearly, right? I mean, it has dips and troughs, and it still needs adjusting, right? So if I do an adjustment and I still need to do more adjusting, that again has this complication factor. It's a different complication factor, but arguably I'd be at my linear regression, and I'd have to just go back to my window moving average method after my linear regression, and that's even worse, right? So there are pluses and minuses. You have to think about your application. Seasonality, well, we saw some seasonal data with the airline passengers example. Here are some other examples. There's two kinds of seasonal data you're usually dealing with. If you look at these, what do you notice as the difference in the seasonality? Exactly, right? And so what they call this is additive seasonality versus multiplicative seasonality. So on the left here, where we sort of have, like you can see the variance is about the same. Really, it just looks like your seasonality is upshifting or downshifting, but otherwise your data is the same, right? The sort of band of values is the same. On the other hand, on the right, we have multiplicative seasonality, where we might have some underlying cycle, but the values changing as the values increase, say your variance is increasing. So you have this multiplier effect in your seasonality rather than an additive effect. In the real world, at least with human behavior, most effects tend to be multiplier rather than additive. But it depends, right? You might have some underlying domain knowledge again. Removing seasonality tends to be fairly tricky. It's not like removing a trend. So the simplest is you just want to average detrended values for a specific season. So you could just have like a springtime adjustment, a summertime adjustment, or like a May adjustment, or whatever your season is for your domain. What's more common, because it tends to work a little bit better, is you use a low-S method, a locally weighted scatter plot smoothing. You might have come across this in other use cases. It's not just for time series. You have a window of a specified width. You have a weighted regression line or curve fit to that data, with points closest to the center of the curve having the greatest weight. So it's not usually an ordinary least squares regression. It's something that's weighted. You reduce on points farthest from the regression line curve, and calculation is rerun several times. So this is very computationally taxing, but it is the way people tend to get rid of their seasonality. So basically, seasonality is very computationally taxing, but you have to deal with it. So you get rid of your seasonality, you get rid of your trends with differencing. What else do you still have to worry about? Seasonality, trends. This is seasonality, but it can also just be increasing variance. Usually with increasing variance, your solution is like a power transformation or a log transformation. So let's think about the things we've got so far. We've got power transformation, log transformation, differencing, linear regression fits. What do we like about all of these things? Python can do them. I like that, right? Or a computer can do them. Python's even better. The other thing I really like is these are one-to-one transformations. So once I fit my model or predict my model, no matter how much I have sort of screwed around with my time series with these functions, I can always go back the other way. So the thing I end up predicting often doesn't look very much like this, the data that somebody handed me and asked me to predict, right? Like my boss says, can you predict chair sales by week in the Netherlands for the next 14 weeks? And I end up deciding that I'm going to do some kind of log power difference transformation in my actual model, but then when I turn around and talk to my boss, I'm going to have to retransform it, right? So transformations are fine as long as they're these sort of one-to-one monotonic transformations. Okay. Stationarity, you're going to test once you think you've got it stationary, right? You want to make sure you've done your best to get rid of the variance changes, get rid of the trend, get rid of the seasonality. Autocorrelation is even harder to deal with, so we won't even go into how you might deal with varying autocorrelation. My answer would mostly be don't, because that means you might have fundamentally different processes. But for these other concerns, once you've taken care of them, one standard way to see, do I have a reasonably stationary time series, is the Dickey-Fuller test. Basically, you just want to make sure, once you can put your process in these terms, that your row value does not have unit value. So this test is just one sort of benchmark. It's a statistical test, right? So it's only giving you a probability. There's no real guarantee that your process is stationary or not stationary, right? You can say I'm 5% certain or 90% certain, and you want to understand what that means. But this is a good benchmark to keep yourself honest, right? If you test it and your stationarity is still terrible and you're still like clearly very close to having a stationary process, you probably want to keep transforming or give up if it's truly not stationary. Okay, so once you do that, you move into forecasting, right? For forecasting, you need that stationary process. Once you've achieved that stationary process, you want to think about how your model is working. So we're going to think about ARIMA models. ARIMA includes two kinds of processes. The first is a moving average process. So a moving average process is defined as having this form. Your value is your mean plus a bunch of error terms going back in time. Mu is the mean of the series. The thetas are the parameters. This is a stationary process regardless of the values of the thetas, right? Because your errors are IID, Gaussian, mean zero, etc. So this is guaranteed to be a stationary process if you've got your moving average, right? Part of the reason we can only model stationary processes is that's the underlying assumption of our model, right? We're saying, if you have a moving average, you'd better be modeling something that's also stationary. If you look at an MA1 process, right, that would mean that you are only using one prior term. and that will have a theta, right? So then that would be your process. Your xt, your current time, is a function of your error at that time plus your error at the previous time. That theta, though, still has quite an impact on what your model looks like, right? So if you look at a positive theta, you'll get this value on the left, versus if you look at the negative theta, you'll get this series on the right. How are they different? Well, the one on the left is smoother, right? The one on the right tends to jump around more, right? So the one on the left is basically saying, well, if I had this positive, right, this is going to be positive 2, this tends to make it bigger, right? If this tends to be smaller, they tend to counteract each other. Versus if it's negative, that's almost like a bit like having a negative correlation, right? It's like saying if this one was high, I'm going to go low. And so you end up with a more jagged, jumpy process. So sometimes even when you're looking at data and thinking about, well, how would I model it, there are more formal tests, but you want to think, well, does it jump around a lot, or is it sort of more meandering? And that gives you an intuition as to whether you have a positive or a negative theta, and also how many terms. So a moving average process is part of your process, but we've modeled it as a combined process. So it's both a moving average and also an autoregressive process. An autoregressive process means that your value at a particular time depends on your value at previous times, right? So here, we're assuming you sort of oscillate around a mean, and then you have sort of an error term at each time, and that error term carries forward a bit. In an autoregressive process, and think about it, autoregressive, regressing on yourself, you are saying that your past values have something to do with your present value, and even the form, right? It looks like my form at time t is, it's almost like a fitted value to a regression on prior values, plus an error term. So if we were to think about an autoregressive process of value 1, then my value at time t is merely a function of my value at time t minus 1 plus an error term. It's like a y equals mx plus b. And again, you can have a positive or negative theta, and you see the exact same thing, that positive or negative theta tends to sort of indicate how much your time series jumps around, right? So if it's positive, it's smoother because they tend to correlate with each other. On the other hand, if it's negative, they tend to anti-correlate with each other. So those are autoregressive portions. And then finally, we have what's this wonderful ARIMA. Where does the I come from? The I is differencing. The I for differencing is just what we would do to detrend the data. So that differencing we did just before, that can actually be done by the algorithm. You don't even have to difference sometimes. You can just tell it, well, difference once, or difference twice, or difference 3 times. Now, to tell it how many times to difference, you have to know it, right? It won't figure that out for you, but that is included. Now, the I in the ARIMA part is really not that important because you can also just do an ARMA model where you've done the differencing. So the I is sort of optional, more record keeping, but the autoregressive and the moving average portion of your model are what's important. So your ARIMA model is the most general class of models for forecasting a time series, which can be made to be stationary. I cannot say that enough. If it's not stationary, this is a no-go. So your statistical properties have to be constant over time. Short-term random time patterns always look the same in a statistical sense, right? So that's what the ARIMA model takes advantage of. You need your autocorrelation function and power spectrum to remain constant. You can do nonlinear transformations to get there, but they have to be monotonic, one-to-one. And from that, you can extrapolate the signal for the forecast. Okay, so how do you apply this, right? We get the magic, wonderful magic stuff from stats models. We don't even have to figure it out ourselves. But we do have to diagnose our model properly, right? To do that, you need to figure out what ARIMA model to use. How many autoregressive terms? How many moving average terms? To do that, we're going to use a plot of the data, the ACF, and the PACF. Remember, the ACF is our autocorrelation function. The PACF is our partial autocorrelation function. With the plot of the data, we're looking for a trend to determine whether to transform the data. And once we've done that, then we start doing tests to figure out the order of the moving average and the autoregressive. One thing to keep in mind, as we're diagnosing, we're going to use the partial autocorrelation function for the autoregressive model diagnostic, and we're going to use the autocorrelation function for the moving average model diagnostic. So each of these plots gives us different information about what we want to use for our ARIMA model. The part that I find easiest to understand is using the partial autocorrelation for the autoregressive. So let's think about that for a second. This is our autoregressive process. Let's say instead of the partial, I just use the full autocorrelation function, and I have an AR1 process. Well, my lag of 1 will have a high autocorrelation, obviously, right? Because my time t value directly depends on my t minus 1 value. But what about my autocorrelation with lag 2? Is that going to be 0, as I would like, because then it's clear cut? Well, think about it. It will be somewhat less, but it won't be 0, because this t minus 1 itself has t minus 2 inside it, right? Because this t minus 1 was also in my AR1 process. So it's sort of like turtles all the way down. This t minus 1 contains all the other values, right, in this autoregressive sense. So I'm not going to use my autocorrelation there. My partial autocorrelation is perfect for this, because all that t minus 1 can explain of t is all that t minus 2 can explain of t. So if I use my partial autocorrelation, the entire explanatory value of this autoregressive process is contained there. And so my partial autocorrelation will drop off steeply. Does that make a little bit of sense? Seems like we're okay. Okay. So that's our ARIMA model. And I just want to point out before we jump into the code that ARIMA models really are everywhere, especially in econometrics, but also in the sciences and the social sciences. It's just a very general way to try to predict time series. But it does have one limitation, which is, A, it's hard to predict the future, but B, thinking about the model. Let's say I come to the conclusion that I have a purely autoregressive process, right? There's no moving average component. An order 1 autoregressive process. And my boss is asking me to predict carpet sales 17 weeks out with my weekly data. Can I do it? I have this week's carpet sales data. Can I predict next week's carpet sales data? Reasonably well, right? If I think this is an AR1 process, I'm going to fill in this value, assuming I fit my model. I can get next week. What about the week after? My error will just keep compounding and compounding, and a few weeks out, I'm just going to have these massive error bands, right? So your error bands are going to be a function of what you think the process is. In this sense, it can be very tempting to have a higher order model, right? Because you think then at least I have more information, right? Like if I have a 6-order model, maybe I can just pack more information in. Do not give in to that, right? Most things are very low order. If you're going to high order because you think it'll somehow narrow your error bands, you are totally wrong. You are just overfitting your data. So keep that in mind. These things have limited power based on the underlying model, and that's just how it is. It's tough to predict the future. If we could predict the future, we'd be billionaires. And some are. Okay. So first, let's play around with some autoregressive and moving average models just to make sure we know how to generate them. Right? So if I wanted to make an AR1, what do I need? I need a phi. I need an initial value. And I just need to set like how many I'd want to generate. So what am I going to do? Well, I'm going to say there's an error value at every point. I've got my time series with my initial value. And then for each period, what do? I append the error plus phi times the value 1 point in time earlier. And that's my AR1 in Python, even with my random error thrown in. If I want to do an AR2, slightly more complicated, but still fairly straightforward. Now I need 2 phis, right? 1 for each value. So I have a phi 1, I have a phi 2, I have however many I want to generate, and I need that initial value, right? Because my first initial value will tell me where I go from there, and I bootstrap from there. So my time series is going to be my error for whatever term period, plus phi 1 times the value 1 moment back in time, plus phi 2 times the value 2 moments back in time. And you'll notice here, because I have an AR2 process, I need 2 initial values, right? Pretty straightforward. So if I do this, and I take a plot, that just gives you an idea of what an AR process can look like. By the way, is this a stationary process? No, right? So the phi's will determine whether it's a stationary process. Not all autoregressive processes are stationary. Okay. And what about A2? Also really not stationary. Not surprising, right? Go ahead, take a minute, try to code up the moving average process. Right, and I will put up that code for the moving average for the slide so you remember what it is. Moving average is a constant average with a sum of previous error terms determining the present value. So how would you do that? Okay, so here's how I did a moving average 1. Again, we need a theta or a phi. I mean, you can call your parameter whatever you like. You have your time series. You have your random error. Now, in a moving average model, your value is really just a function of the prior error plus your current error, right? You're just sort of accumulating errors or doing a moving average, literally, of those errors, and that's your value. And then if we look at what our moving average plot looks like, we see something like this, right? So this one is by definition stationary, and it's going to sort of oscillate around whatever that mean value is. So let's look at that autocorrelation and partial autocorrelation for each process. So if we look at an autoregressive order 1 process, here's our autocorrelation. 1 for itself, and then still significant at 1. Arguably still significant at 2. Why is that? I know it's an AR1 process, but it's showing up like an AR2 or AR3 process. Just not enough data, right? Like I still will have some statistical uncertainty. The fewer points I have, the less certain I can be about what my underlying model is, right? There's just going to be some sloppiness. And here's my partial autocorrelation function, right? This is the one that really matters. Remember we talked about with an autoregressive model, it's the partial autocorrelation model that's going to fill in the parameters. This one is rock solid. It's not always that way, right? I can still have statistical errors. You'll notice here, for my autoregressive value of 1, I have a significant term, or my lag of 1, but not after. That means that it's only the lag of 1 that really explains a correlation or variation as I look at my partial autocorrelation. So that's autoregressive, right? For my autoregressive diagnostics, I look at my partial autocorrelation function. Okay, what about my moving average? It's kind of the inverse mathematically, and I'm not going to prove it to you today. This is very standard stuff. You can look it up. For moving average, you expect the autocorrelation function to show you where you should cut off your model, and you expect the partial autocorrelation function to just sort of taper off. So let's look at that partial autocorrelation function, and we see here it's not very informative. We're not expecting it to be. We ignore the partial autocorrelation function for the moving average, and we use the autocorrelation function. And here we see we've got one term at here, right? There's our 1, and everything else sort of falls in the band, and here again I've got some error, my series wasn't long enough, right? So this is where your domain knowledge still comes in. These statistical tests will give you some pointers, but at the end of the day, if you have a sense or a domain knowledge of how your process works, that's really the best. Okay, so we've done our model diagnostics, or we've learned how to do them. Let's actually do some forecasting. So if we do some forecasting, let's go back to that air passengers data, right? Let's say we're an airline and we really want to figure out how airline passengers come into being, right? What the underlying process is, because once we know that underlying process, we can sort of try to make a few predictions a short period of time in the future, right? We don't want to go too far in the future because, of course, we just rack up lots of uncertainty. So we'll look at those air passengers. We're going to do a log transformation because we had noticed that the variance gets bigger and bigger right over time. So trying to get to a stationary process, we're going to log transform. It's 1-to-1, so it's easy to backtrack. We're also going to difference it. And if we look at this difference logged process, it looks okay. Have I removed the seasonality? I'm not sure that I have, right? I mean, I think I still sort of see patterns. I'll worry about seasonality later. Let's sort of ignore that bugaboo and just see if we can start predicting. So one question for you, though. When I differenced, what did I lose? What information? The Empire State Building is 200 feet taller than the apartment building I live in. Do you know how tall either building is? No, right? So you lose the information about the mean. That's fine. You can recover it. But it's one thing to think about, right? Is for ARIMA, you're really just looking at a mean of 0. The absolute number doesn't matter and shouldn't matter. Okay. We're going to just drop our NA. And we are going to run our AD Fuller test. This is the sticky Fuller test we talked about for stationarity. We want to make sure that we have a stationary value. And what do you think? So our critical value for 1% certainty is minus 3.4, for 5% minus 2.8. I'm actually only at 0.07, so I can't reject the hypothesis that this is not stationary. That stinks. It shows that you can do a lot of transformations and not be entirely sure. We're going to leave it at that for now, but you probably wouldn't want to proceed with this time series normally with this model, right? And it just goes to show that stationarity is not that easy to achieve. That said, given how few data points I have, and given I've already run 2 transformations, I don't really want to keep differencing, right? I can difference and difference and difference, and I will eventually get stationarity. It becomes kind of ridiculous, right? So that's another thing to think about. You might apply the model, know that you are not quite conforming to the assumptions, but at least still have some basic intuition about what you're modeling versus following the letter of the test, but not necessarily modeling something intuitive. Okay. We're also going to do our diagnostics on this data, right? So we just did diagnostics on theoretical AR1 and MA1 models to see what they should look like. Let's see what some real data looks like. So we've got our stat tools. We're going to compute our ACF and our PACF, and we are going to plot them. So this is my ACF. What do I see here? Well, I've got some seasonal data, which is why I've got this thing at 12. I'm going to ignore that for now. And just notice I've got a lag of 0 and a lag of 1 is significant. And I'm only going to look at the first time it crosses that line for significance. And I'm going to say, well, that looks like, for an autocorrelation, that suggests to me an MA1 process, right? It's a process where the first lag matters and then it drops below significance. And this I'm going to chalk up to seasonality for the time being. I'm also going to look at the partial autocorrelation function to look for my AR term, right, my autoregressive term. So this was my moving average term. Now I'm interested in my autoregressive term. And here it's a little dodgier, right? So again, this stuff out here I'm going to chalk up to seasonality, but after my lag of 0, I have a lag of 1, which looks significant, right? That is above my sort of rule of thumb significance dotted line. My 95% confidence interval. This one is just on the brink. So I'm sort of thinking this looks like an AR1 or an AR2 process. I'm not entirely sure. Personally, if I think about airlines, well, I could see that the month before would correlate, but I could also see that maybe 2 months before would be important, especially because people don't tend to just buy tickets, and use them the next day. There tends to be some lead up, so it wouldn't be surprising if 2 months were also a useful amount. So I'm going to keep that in mind as I look at my model. I'm going to import my ARIMA model, and I am going to play around and see how things look. So an ARIMA model has a PDQ. The D is the differencing, right? So how many times do I want a difference? I happen to think that one differencing term is nice, so I stick with that. The P is the autoregressive component, right? So it's P, D, Q. For now, the Q, the moving average component, I'm just going to look at 0 because I want to see if I just model this as an autoregressive, right, trying to be as parsimonious as I can, how does that look? And see how that looks. And I'm starting with the autoregressive because it very clearly has some autoregressive component, right? The moving average component I can always sort of throw in. The autoregressive bit, though, is very clear, partly because I had a trend in the original data. So if I graph that, I've got my red as the fitted values, my blue as the true values transformed. It's okay. I've got a sum of square error of 1.5, which doesn't really mean anything per se until I start comparing with other things. So now let me try a model with a moving average model and see how that does, right? So I get rid of the P term for my autoregressive. I have one difference, right? That's just intrinsically there. And I do a order of 1 moving average. I guess that looks okay too. I mean, they sort of look about the same, and if you look at the sum square error, they're about the same, right? So it's not clear that either of them is doing such a bad job or such a great job. I can try to combine them. So now I have an autoregressive model of order 1 with a moving average model of order 1. Let's take a look at this. The sum square error is a little bit better. As we can see, it's dropped down to 1.45. Not necessarily that much better, disappointingly. But I'm going to sort of call it a day there and go back and map it to my original data and think about how that does. So let's go ahead. These are our predictions. We're just backing out to our original form of the data. And now let's compare that. So the ARIMA model with, let's go back and see what we did with the 1, 1, 1, that's what we settled on, gives us this, right? So it captures the trend when we untransform it, captures the trend, but it doesn't really capture A, the seasonality, or B, the change in variance, right? Why is that? Should I expect it to? Not really, right? So, Right, so there's this multiplicative aspect that I haven't accounted for the seasonality, and also the fact that I'm really trying to model a stationary process, right? So with an ARIMA model, I differenced it, so I dealt with the trend, I can build that back in, but I didn't really factor in the changing variance and the changing seasonality. So that is sort of the limit of a basic ARIMA. From here you can go to a seasonal ARIMA. What you do with a seasonal ARIMA is you basically decompose your model into a seasonal component, which has its own moving average and autoregressive term, and a non-seasonal, which is what we've done here. That would be your seasonal. So this is about as good as you can do with like a plain vanilla ARIMA. Why is it useful? Well, it's still useful because you've still got the underlying trend. You've got some model for how it works, so you can try to develop some insights from that. And you also sort of can see exactly where you would put the seasonal bit on, right? So if you don't want to do a complicated seasonal ARIMA where you'd have 6 parameters rather than the 3 we already have, you could even think of sort of doing your own additive model here combined with your ARIMA. So the ARIMA can be combined with other models. So no more, we're not going to follow up, but I'd very strongly recommend looking into the seasonal ARIMA just to understand how it works and also things like confidence intervals, etc. So I'm going to leave the ARIMA here. We have 30 minutes to cover time series classification. We're going to take a 5-minute break and then finish off with that. So we'll reconvene at 4:09. So let's get started. The last thing we're going to talk about today is clustering and classification of time series, which is yet another route to prediction. For those of you who work in areas related to machine learning, this will probably be very familiar because it uses many of the same techniques and just applies them to time series. So clustering and classification are especially interesting because they deal very well with the regular time series, right? So ARIMA assumes you have this stationary world. It assumes you have this non-seasonal world until you put in all these fancy modifications. And it assumes you have regularly sampled your data, and they sort of mean the same thing across time. If you have a regularly sampled time series, one very intuitive, straightforward way to sort of deal with that is to think about how they relate to each other and use that as a way to predict, right? So I can look at a time series and I say, well, what does this time series look like based on what I've seen? And the one it looks most similar to might be a really good way to predict it. So we're going to be thinking about how we do that, how we look at sort of the whole time series and relate it to other time series. To do that, for those of you who know a bit about clustering, right, and comparing things, when you want to compare things and determine how similar they are, you need some kind of quantitative measure of how similar they are, right? Like, if I want to say how similar are people, I could say, well, if you have the same gender, I'm going to say you guys are identical. That could be one metric, right? Or another metric would be a measure of similarity between people is I'm going to take the difference in their weight and square it and to that add 3 times however many miles apart they live from each other, right? There's like many ways you can come up with a metric to compare things. For time series, it might be very tempting to just use, say, Euclidean distance, right? Because you say, well, it's not like people where they have all sorts of different kinds of features. It's just a time series. What's so complicated about comparing these? Well, let's first let me ask, which of these two are the most similar? Right? I think all humans will agree. Which of these are most similar? Which of these two time series are most similar to each other? The green and the blue. Does anyone disagree? Anyone at all? No, right? I mean, it's so obvious, right? It's so stupid I'm even asking this question. And yet, if you use Euclidean distance, those are not the most similar, right? So this is the proof that you don't want to use Euclidean distance when you're comparing time series, okay? If you use Euclidean distance, it's actually the blue and the red that come up much closer together for some reason than the blue and the green. So there's your proof that you need a better distance metric. What is that distance metric? The one that seems to work really well and that is fairly intuitive, and it might even be what our brains all did when we decided those two time series were the most similar, the two signs, is dynamic time warping. What you do with dynamic time warping is you line up two time series next to each other, as we do here, and you try to make them similar to each other by saying, okay, for this time series, to compute the distance with the next one, I'm going to give it sort of the closest, best match I can, so that for each point, I will just pick the point in time that best matches it. And that could be, for example, in this case, right, of this green, we see like one inkling you can get is like this sort of curve here or this kink. I probably want to match it up here. To match this up, that means this first point has to match up to a couple of points, right? So it's sort of like a shape-shifting way of matching things up. You sort of shift your time series, like imagine these are my time series, right? I want to sort of shift them until they match as well as possible. And this is a very pat example, but you get the idea. I'm going to move them around, but it's not just that I shift them, and that's why the word warping comes in. I can also shift the amount of time per time series, right? So I see here between the green and the blue, if I condense these 3 points into one on the green, I'll get a much better match later. So I do this search to find the way to line up points, including compressing time to 0, such that I can match them best. And you can see that sort of grid layout here. This one, time doesn't move, whereas for this one, it does move. So that's dynamic time warping. That's the distance metric, is first I line them up, and then I compute it. Why is this great? Because I have a distance metric that works the way our brain works. For example, this blue and the green will now be closer together with this dynamic time warping. because I can sort of shift them to have that sign shape reflected in both of them. And I can also do nearest neighbor classification and clustering. So let's go ahead and get started with that with some code so you can see how simple this is. We'll go to Notebook 10, Clustering and Classification. Don't worry too much if you don't have these functions. I don't actually think you need them here. We're going to read in a CSV, which has actually the words as time series. So people speak words. They're recorded as time series, the inflection in our voice, but we all say them a little bit differently. And we have 50 different words. As you can see, they're just labeled word 4, word 12, word 13. Let's take a look at some of them to see what I mean here by our time series. Here what you see is I'm actually grouping the words by their value and taking the mean. So these are different kinds of words. Let's take a look at word type 7. This is what the average word type 7 is. I'm sort of at each point in time, I'm averaging all of the 7s. And let's take a look at what just one of them looks like. Right? So this is sort of an idealized time series I've come up with by averaging all of the spoken words of a certain type. But this is really more what my data is going to look like, is something like this, something kind of fuzzy. What about the full sample of all these words? Well, that's here. Right? So word type 7, you can see they all sort of follow the same shape, right? They have one bump, and then they have a second bump, and then they have maybe 1 or 2 bumps in the middle, and then they have a bump at the end. And as you can see, though, there's like some outliers, like this blue one here, which it almost seems like this person is speaking a different language, right? They don't even have the same number of rising and falls. And this gives you an idea of why computers recognizing what people say is so amazing, right? Because we all say it differently to quite a large extent. So the first thing we need to do is code up a sensible distance function, right? And that's that dynamic time warping. I won't make you do it. I'll just load this snippet here, and we can take a look together. So we're going to define this DTW distance between two curves. We're first going to just set the distance at each point to infinity, and then we're just going to go through, and for each point, we're going to try to find a way to match them up so that we minimize the distance, right? So for every point in the first time series, for every point in the second time series, we try to compute that distance where we're sort of minimizing, right? We're getting the minimum of either moving one forward, moving another point forward, keeping them matched up, and getting that minimum distance. So that gets our dynamic time warped distance. Once we have that distance, we can start computing differences, right? So here I just pick randomly 2 words. I just grab them out of that data frame, and I'm going to compute the distance. It's 6.6. That doesn't really mean anything on its own, though, right? So unlike Euclidean distance, dynamic time warping distance is only meaningful in the comparative sense, right? And in that sense, it's not a true distance metric, right? Like Euclidean distance means something in an absolute sense. Dynamic time warping only means something in a comparative sense. So we can look at some distances, and we can plot. So here we've got 3 curves. Let's see. Two of them are quite similar, right? The yellow and the red, which is S1 and S2. S3, the black one, is fairly different from the other two. And so let's see if that is borne out by our metrics, right? So S1 to S2, red to yellow. Which one is it? I didn't compute S1. Oh, yes, we did. 6.6, right? S3 to S1 is 11.1. S2 to S3 is 10.5. So far I'm satisfied with this metric in the sense that S3, this black one, is showing up as more distant from the yellow and the red than they are from each other. So we say, okay, at least the ordering of this distance makes sense, right? Okay. On the other hand, if we look at the Euclidean distance, which I won't make you code out, but there would be our Euclidean distance. If we compare the values here, so S1 to S2, right, those are the two that are similar, versus S3 to S2 and S1 to S3, well, S3 to S2, those are supposed to be far apart, and the Euclidean distance makes them far apart, but S1 to S3 is almost comparable to S1 to S2. And here's another example of why the Euclidean distance failed. So this I truly generated randomly. I wasn't even sure that it would fail when I first put this example in, but it does. So that example in my slide is not necessarily all that artificial. Euclidean distance will often lead you in the wrong direction. So let's think about, can we classify a random row by determining which mean curve it is closest to, right? So we looked at the variety, for example, of words, right? These are all the exact same word. We see quite a bit of variety, but we also saw that we could take a mean or a median of all of them, combine that, and get some sort of mean shape per word. So first reasonable question we can ask is, can we sort of use this distance metric to figure out for an individual messy data sample, which idealized form is it closest to? And is that a good way of classifying a time series? So to do that, we can first compute that mean curve, right? So for each word type, grab all of the examples, take a mean, and say that's my idealized word, that mean type. So that's what I've done in this code here. I'm going to just randomly grab a test word. Boom, I've done my test word. In this case, my test word is of type 5. I'm going to calculate a distance dictionary where I calculate the distance from my test word to each of the idealized forms of the 50 kinds of words I have. So I'm going to do that. It's probably going to take a little while, right, because it's not super fast. Okay, that has run. And now I'm going to do an ordered dict. And look, lo and behold, when I run my dictionary and sort it, on the left I have my word type, on the right I have my dynamic time warping distance, and I randomly picked a type 5 word. Lo and behold, the closest thing is indeed the idealized curve of type 5. Great news. Is it the best possible news, though? What do you guys spot here? Type 36 is also awfully close, right? So in this particular case, it worked out. Can I guarantee that it would? No. Classification and clustering are not perfect, but this is how you can do it, and you have, a pretty good shot of matching to what you want. So that's one thing you can do, right? This is that nearest neighbor classification, right? Which of these idealized types is nearest to my actual data sample? Another thing I could do is I can say, well, this is kind of computationally taxing, right? Like this is a very small data set, and it still took a little while on my computer, right? Like it didn't instantly compute, which is already kind of scary on such a small fake data set. So you might say, well, can you cluster the words using this DTW metric, right? This dynamic time warping metric, where instead of calculating the distance to idealized forms, can I calculate all of the words and just sort of organically cluster them? Yes, but that would take more time, at least on my little computer, than we have. I mean, I tried running it once. It took more than 3 hours. It's kind of an old computer, but you can do that at home if you want to. What you can do, though, in the real world, if you start running into situations where you have lots of time series of different shapes and you want to start matching them, is you can do clusters based on features rather than clusters based on dynamic time warping, right? So there are many different ways to define distance, and this is actually where we go back to treating a time series like a person. Remember how I talked about how there's different ways we could measure distance between people? One way to do it would be to use features, and this is very common in large data sets. In reality, so dynamic time warping is sort of what you might do in a perfect world, but in reality, feature selection is so much faster and so much sort of more intuitive when you're trying to explain the model that people often go with feature selection. A nice thing about feature selection is it also gives you more opportunities to incorporate domain knowledge. So dynamic time warping is more sort of automatic, right? You just sort of match things up and you sort of warp time to make them fit each other. But that doesn't give you the opportunity to say what you know about the subject, right? Whereas if you're an astronomer or you're a business retailing forecaster or you are a stock trader or whatever, you might actually know quite a bit about what matters in the performance of a time series, and you can extrapolate that. So, for example, in this particular case, we could go back and we could sort of look at a sample of the words, even as not domain experts, but a couple of things jump out at me. The inflection points are really important, right? The location of the max is really important. If I start thinking about where this purple differs from this blue, well, the max for the purple is early. The max for the blue is a bit later. The purple seems to have, 1, 2, 3 local minima, whereas the blue also has 3 local minima. But this green one only has 2 local minima, or maxima rather. So I start seeing ways in which these series are different, and I'm going to just generate features based on the way they're different. So a few things I'm going to pick. I'm going to look at the max location. I'm going to look at the first local max, the second local max, assuming I have verified there's always at least 2. I'm going to look at the total number of inflection points, right? So something very bumpy versus just kind of bumpy. I'm going to look at the ratio of the first local max to the absolute max, right? I'm just adding things to make sure I have enough to distinguish these 50 kinds of words. And I'm just going to put together vectors of all of these qualities. And I'm going to make a data frame out of them. And here's what I see. So my first local max for just my first recording is at 23. My max location is at 187, etc. The word type is the label, right? So that part is what I know to be true. I'm going to actually leave that out now that I'm going to try to do some clustering. I'm going to just do a k-means cluster. You can do all sorts of clustering, right? I'm going to look at those labels. And I'm going to just see how I did with this clustering. So let's see. This is my word type and my label. My labels don't need to match in the sense of like a 5 for my clustering is not a 5 for my word type. But what I do want to see is whether all of my word type 5 ended up in the same cluster. And what am I seeing? Well, I'm seeing that they didn't all end up in the same cluster. That's not surprising. When you work on real-world data, it's usually not perfect. I am pretty happy that there seems to be a lot of 37s, a lot of 2s, a lot of 6s. So I made 50 groups in my model, and my model came back and took one group and broke it up into 3 clusters, I guess. That's not so bad, right? That's probably quite understandable given the amount of variation that I see, right? And the way that we saw that this blue was the same word as this turquoise. It's hardly surprising that they didn't end up in the same cluster. But I get some sense that the clustering can accomplish something. So that's a straightforward example of how you can deal with time series when you maybe have irregular time series data, or where maybe you just think that the shape is more important than the actual data points, right? So for an ARIMA, you're sort of looking very finely, right? You're sampling regularly. You are making a stationary time series that might not even look like your time series, and what do you get out of that? You try to predict a little bit in the future, maybe 1 period in the future, or 2 periods in the future. With time series clustering and classification, you can do irregular time series without having to upsample and downsample and sort of impute data or make up data in some way. You are also emphasizing something that's slightly more intuitive, right? And for certain domains might make more sense, like astronomy or human behavior. It might make more sense to think, well, does it look like this or does it look like this? And there might be some underlying reason you care. In that case, you're going to go more for clustering and classification. And clustering and classification in particular is very transparent in a way that the ARIMA model sometimes isn't, right? So ARIMA has 3 parameters, or if you do seasonal, it will have 6 parameters. It does this very complicated maximum likelihood estimator. You get back these numbers. You can really only predict 1 or 2 periods in advance. In contrast, if you can cluster a time series just based on an early portion of it, you might have a much better idea of what your later portion of your time series looks like, even though it's still very distant in time. So that can be an upside of clustering and classification. So I just want to talk briefly about some other things you might want to look into if you are interested in time series. The first is vector autoregression. I actually had a question about this during the break. What if you have regularly sampled data of many kinds, right? So we did an ARIMA model where we just had 1 time series. In the real world, you are often blessed with abundant time series in parallel. For example, you might want to predict unemployment in the US economy, and you have all sorts of info. You might have your consumer happiness index, you have the price of bonds, maybe you have some global economic measure, all of these things regularly sampled, and they all tend to predict each other. You can take advantage of that structure, and as you can see, it's an autoregressive model, so it's very similar to the ARIMA model we looked at. It's just that much more fitting and many more parameters because now you're using parallel data sources. So that's handled in stats models. If you have that kind of data, that's probably what you want to start with. Very common in econometrics. Standard workhorse is used all the time. Common filters and filtering in general, signal processing in general, right? That's really just time series. If you work on the sort of data where you are handling live data and you are trying to track a process that is moving as you track it, common filters and other sorts of Bayesian filter methods are probably what you're looking for. With these sort of methods, what you do is you take the information that you have, you sort of update what you know about the system, you make a prediction, then you measure the next prediction, you update what you know about the system, you make a prediction, you update what you know about the system, and it sort of feeds off itself in a live format. So that's common filtering, another area that you can learn more about, and that is handled in many Python libraries. Hidden Markov models. These are very common, especially in the sciences. With a hidden Markov model, what you say is, I have a time series. It has some kind of observable, but it's not the thing I'm actually trying to measure, right? The thing I'm actually trying to measure is hidden. So this might be, for example, you work in biology and you have some kind of cell that can be in, let's say, 5 different phases. And depending on which phase it is, it gives off maybe a different level of some hormone, right? And all you can measure is the hormone. You can't actually measure the underlying phase, right? That's sort of hidden information. This is what you're going to do with a hidden Markov model, is you have a way to try to back out what phase something must have been in based on what you saw. So this is sort of an ex post model. You're not going to use this for forecasting, but you will use this if you think there was something hidden and your time series only gave you a partial indication of what that was. So you can use HMM Learn in a situation like that. And then finally, the thing that scares me most is deep learning, because there's always the possibility that deep learning will just eat everything else. So I feel almost like I need to make a disclaimer about my whole presentation. People are having tremendous success with recurrent neural networks, both in natural language processing, which is arguably a kind of time series, and also with time series prediction. It's still in early days, but I have a feeling that ARIMA might get blown out of the water, or time series classification can easily get blown out of the water with this. So this is something you definitely should keep an eye on, but it is still very good to understand the traditional methods. And then finally, as far as more resources, so this is sort of like a bird's eye view of time series and time data. There are a lot of really great resources out there, so these are just a couple of my favorites that I would recommend as like next steps if you want to keep working on time data. So that is the end of my presentation. Thank you for coming, and I will hang out if there are questions. Yeah, so the slides will be available as soon as the PyCon folks post them, and if there isn't a formal PyCon route, I will also put it on the initial Git repository that you downloaded from. So those I'll put up actually later today.